now it's okay, sir?
It is not full screen, ma'am. Still, it is in the normal mode.
Or otherwise, can make it slideshow mode. In the
Slideshow
top,
mode,
there
yeah.
is some slideshow.
Sir, screen moving, sir?
Madam, screen is not moving. That is what we asked him to put it in a slideshow mode.
Sir, now it's okay, sir?
Madam, your screen is visible. Can you do one thing? You bring your cursor, the bottom line, and there was a symbol called similar to cup symbol is there, no? Can you press that? Can you move your cursor?
Yes, sir.
No, in the bottom, madam. The bottom of your screen. Not there, madam. Bottom, not here, down.
Shall I continue, sir?
Madam, your screen is not visible. Kindly share it first,
How much,
ma'am.
sir?
The screen is not visible, madam. Kindly share the screen.
So now? Shall I continue, sir?
Continue, madam.
It is okay. You can continue, please.
Quality, then substitute quality control is defined as an economic effective system of maintaining and improving the quality of output throughout the whole operating process of specification, production, and inspection based on continuous testing with random samples. The quality control relies on statistics and the data report and assess quality, and is therefore an effective means to evaluate the manufactured product to maintain the consistency of the product is made. The main focus of the statistical quality control is the dry statistical technique, which would help us in separating the observable causes of variation from the sound causes of variation, thus enabling to take action whenever observable causes are present in the production process. In production process, our main aim to control the maintain and the quality of the manufacturing product during the production, that is to conform to the specified quality standards. The method used which are called the process control technique. This generally through the technique of control test developed by Prasad. The statistical quality control divides into process control, the product control. Process control means controlling the chart. The chart control charts for variable and control charts for attributes. The product control means controlling the quality of the product after its production by critical examination at the point mainly achieved by using sample inspection. The product control is using acceptance sampling plan. Here, acceptance sampling plan, then a decision must be made to accept or reject a group of the plot or item based on the quality found in the sample. Here, for the acceptance sampling for variables and attributes. Here, in this table, the acceptance sampling plan is used acceptance sampling plan, A for single sampling plan, double sampling plan, and multiple sampling plan. So single sampling plan. Single sampling plan is to take a random sample of size small n from the lot size and they inspect all the items of the sample that defect found. Here, number of defective D less than C, then accept the lot, then greater than C, reject the lot. Then for double sampling plan, here we using two sample size number N1 and N2. First, count the number of defectives from the first sample size small n1 and denote it as D1 if defective. D1 less than or equal to D1, then the lot is accepted based on the first sample and if D1 is greater than or equal to C2, the lot is rejected for the first sample. If C1 less than D1 less than C2, then the second sample of the size N2 is drawn and the number of defectives D2, the sample is observed. If D1 less than D2 less than or equal to C2, then the lot is accepted, otherwise rejected. Then we call for multiple sample size. Then multiple sampling plan is an extension of double sampling plan, and more than two samples are needed to reach the conclusion. The sample of size N1 is drawn from the lot of size capital N and the number of defectives D1 in the samples are counted. If D1 less than or equal to A1, then the lot is accepted, and if D1 greater than or equal to R1, then the lot is rejected. Then A1 and R1 are the respective acceptance number and the rejection number based on the first sample. If D1 less than D2 less than R1, then another sample is drawn from the lot. The procedure used in the first sample is repeated sample by the sample if the subsequent samples are needed. Then consider reliability concept. Reliability concept is written as the probability that the product, system, or service will perform if intended or function adequately for the specified period of time, or will operate in a defined environment without failure. An acceptance sampling plan under which a sample inspection is performed by the conductive light test upon the sample product may be termed as reliability sampling plan. In reliability sampling, various components is there. The mainly we consider probability of success, durability, dependability, quality over time, availability to perform the function. Mainly reliability means how quality changes over time. The lifetime of the product is the main characteristic of interest sampling plan designed for testing the acceptability of the product. The quality means how will an object perform its proper function. The reliability means the object maintains its original level of the quality over time through the various conditions. Then using in reliability considered like this, here consider methods of the product is expected to be high, so the life testing experiments are usually terminated before a prefixed time denoted by T0. This type of test for evaluating the lifetime of the product is called the considered life test. In the considered life test experiment carried out the lifetime of an item. The following strategy used for the considered life test. The units are specific for life test. Several distributions reasonably well model the product life. It is most likely taking into account the consumer risk, benefits, and the smallest number of units needed to test. As a result, it is employed the definition with the minimum sample size. In reliability assessment sampling plan, based on the conductor letters, needs to make a decision on the lot based on the number of failed items before the experiment ends. In this, the failure that is success and the non-failure that is failure of the product are considered as an outcome of the trial. In particular, classical binomial distributions consider only success and failure cases. Sometimes sampling plan does not need to make a decision of failure acceptance or rejection, but at least lead to indeterminacy. In such the case can be handled by microscopic statistics. In microscopic statistics was founded by Florence New Mexico University, United States in 1998. Microscopic statistics is a generalization of classical statistics and is based on the data that concentrates on the neutralizing information that is present in the part of the data. In classical statistics, all the data are determined. This is the distinction between microscopic statistics and classical statistics. In many cases, when indeterminacy is zero, microscopic statistics coincide with classical statistics. We can use the microscopic measure for measuring the indeterminate data only. In probability, the indeterminacy is different from randomness. While classical statistics is referring to randomness only, microscopic statistics is referring to both randomness and indeterminacy. In operating procedure for microscopic statistics, let you see the universe of disparate in microscopic set A is an object having been A equal to the TA. Here TA means chance that the event X occurs. Ik of X means indeterminate chance that the event occurs or not. Fa means chance that the event does not occur. That's a function of CIF to define respectively the degree of membership, the degree of indeterminacy, and the degree of non-membership of the element X belongs to U. So the set A if the condition is below. It defines that X is space of the point, that is object, which is element in X denoted by small x. The interval microscopic set A in X characterized by the two membership function, indeterminacy membership function, and the falsity membership function. For each point X, that is TA of X, IA of X, FA of X, subset of 0, 1. The microscopic statistics are generalized form of interval perceived statistics handling membership, trueness, non-membership, falsity, and indeterminacy as independent terms. Microscopic statistics is concerned with indeterminate data and it takes into the account the probability of acceptance, the probability of rejection, and the probability of indeterminacy. It's generalized of classical statistics. We administer with the specific values of classical statistics in microscopic statistics. The sample value choose population with uncertainty environment. When microscopic numbers have a standard form based on the classical statistics, it is given below. X of microscopic statistics that is equal to E plus I. Here, E and I, E is the Z or determinant data and the I is the uncertain or indeterminate part of the data. It is equivalent to Xn belongs to X of lower and the upper case. The subset of N is used to distinguish the microscopic random variable, for example, of X microscopic. Review of literature. In microscopic acceptance sampling plan, first used Florence microscopic 2014. After that, Aslam et al. In acceptance sampling plan, introduced monitoring the variability in process using microscopic statistical interval method, and Aslam 2019 a new attribute sampling plan using microscopic statistical interval method, and Devdutta and Balamundi 2020 a new attribute sampling plan for assuming equal distribution third lifetime using microscopic statistical interval method. In microscopic statistics. It considers reliability assessment sampling plan based on the truncated life stage, and it targets an outcome of the trial where the product success and the failure determined before the experiment time. The particular classical binomial distribution considers only success and failure cases. Whereas the sampling plan does not only decide the acceptance or rejection, but it also leads to the indeterminacy case. So, which is managed by user-scoring statistics. In a single sampling plan, are selected in a random manner from the computer's loss. The loss is accepted with the number of defectives or leaks, then the specified acceptance number which are otherwise rejected. In microscopic, single sampling plan deals with the probability of acceptance, probability of rejection, and the probability of indeterminacy. The main goal of studies in inspection is result may lead to indeterminacy and the situation. How can this problem and give the proper solution for the satisfying the both producer and consumer needs? The operating procedure for single sampling plan for microscopic statistics. The inspection process has indeterminacy output in addition to acceptance rejection. If the sample has defective items more than the acceptance number C, the loss is rejected, whether it has more or less indeterminacy item of is I. If the sample has a defective item less than or equal to acceptance number C, the loss is accepted, whether it has a less indeterminacy item. And if the sample is defective item less than or equal to acceptance number C, the loss is indeterminacy, whether it has greater than the indeterminacy item. So, operating procedure for step 1. The decision is made as to which value to use for the measurement of mu naught. Here, mu naught is a specified mean value. Then T naught is a pre-defined testing time, and indeterminacy I of T. The criterion that makes sure that the number of outcomes that result in an indeterminacy is T, specified as T, is compared with IT, if the indeterminacy plot being added IT greater than or equal to T. In step 2, if B less than or equal to T, accept the lot, then the cases in the lot have indeterminate form. I of T less than or equal to T, otherwise reject the lot. Whereas D is denoted by the number of failure occurs. As a result, the failure time of the lot is exactly equal to 2 lifetime of the lot, mu n, specified by mu n. The product does not meet failure time after specified mean lifetime, and it can be classified as success, item, or non-defective. Then, use the distribution for generalized Pareto distribution. It proposed the model of microscopic variant of classical Pareto distribution, useful of analyzing indeterminate or imprecise data. The structured form of the proposed distribution is skewed to the right and determined to the unimodal. The cumulative distribution function of generalized Pareto distribution is given below. Fn of S that is equal to 1 minus rho of microscopic divided by S for the power theta of N. Here, theta is a shape parameter and the rho is a scale parameter. Then the probability density function of microscopic distribution is given below. The mean life of generalized Pareto distribution is expectation of xn equal to theta n rho n divided by theta n minus 1. Then rho n is the rho of microscopic, that is the formula is given below. Then cumulative distribution functions can be written as f of x that is equal to 1 minus mu n into theta n minus 1 divided by alpha mu naught theta n whole to the power theta n. Here mu n, mu naught equal to or M. It represents the ratio between the two mean life and the specific mean lifetime. The probabilities of cases using Newton's interval probability, here probability of failure, probability of non-failure, probability of indeterminacy. The total probability for the three cases are greater than or equal to 1 for the fixed known value of A, theta, and the computer value of PF and non-failure. Probability of failure, probability of non-failure, probability of indeterminacy using this formula. Using this formula, then the operating procedure for neutrophobic single sampling size in generalized Pareto distribution. A decision is made as to which values used for the measurement of theta naught, mean lifetime, specific mean lifetime, T naught, pre-defined testing time, and the determinant. The criterion makes two such a number of outcomes that result in an indeterminacy case compared with indeterminacy for being added if indeterminacy of total greater than or equal to 3. If these less than or equal to 3 accept the loss when the cases in the loss have an indeterminate factor. Otherwise, reject the loss. If these denoted by the number of failure occurs, as a result, failure time of the loss is exactly equal to 2 lifetime of loss. The product does not meet failure lifetime after the specified percentage lifetime, and it can be classified as success item or non-defective item. So, probability of acceptance, probability of indeterminacy, probability of rejection. The statistical interval method follows the characteristic parameter of notation for CA, CI, CR. Probability of acceptance, probability of indeterminacy, probability of rejection. Use this formula. According to the proposed plan, if the number of failures is less than or equal to 3, which indicates the extent of indeterminacy, then it is obvious that the loss will be accepted. And in the indeterminacy of T is less than or equal to indeterminacy K of T. That is indeterminacy for T less than or equal to IC. Then we go for the numerical illustration. We consider real-life data was recorded from law list 2003. In this study, the failure time for failure lifetime for stable installation using method of an accelerated life test, then 10 specimens of each type tested in ordered failure time in R are given below 5.1, 9.2, 9.3 like this. The maximum estimate of the K parameter for the data in this study is estimated to be theta, that is equal to 0.82057. That is approximately 1. The data from the analysis shows that there is 2 failed cables out of 10 cables installation, 7 cable installations that are not failed out of 10 cable installation, and 1 cable installation belongs to the indeterminacy group of 10 cable installations. The operating characteristics value of the probability of acceptance, probability of rejection, and the probability of indeterminacy. In this case, lot of acceptance indeterminate and the rejection properties are given below. Hence, the chance of acceptance lot of cable product is 4%. In conclusion, in this paper, we discuss the concept of new single sampling plan based on the truncated light test using generalized Pareto distribution. This proposed sampling plan will be very useful to producers even if they does not reject the sample immediately, and will definitely protect the consumers at a limiting quality level at the same time. There has been need to provide another opportunity to the producers to consider the indeterminacy case. In the proposed plan, so the producer samples would have another sound. Due to uncertainty environment in which sampling will be conducted, the proposed sample plan will be more effective and appropriate if presented using neuroscopic sampling. These are my references. Thank you.
Thank you,
Sir?
madam. Thank you, madam Jayalakshmi, madam.
Thank you, sir.
There are some disturbance in your voice. I don't know why. There is some noises coming behind you. I think some fan is standing behind you. It's not that much clear. But anyhow, thanks for your talk. Now the forum is open for any discussions, one or two questions. Any people who are working related to that can. Professor Ganesh sir is there.
Yes, I have one question.
Professor. Yes, sir. Yes, sir.
I have one
Please.
question.
Yes, Professor.
Yeah, thank you very much, sir. Thank you, Dr. Jayalakshmi. A nice presentation. Nice presentation. My question is, what about the acceptance sampling number and the probability of acceptance? Did you try for calculation of this? Hello?
Yes, sir. Sorry.
Am I audible?
Yes, sir. Yes, sir. So, probability of acceptance number.
Yeah. What about the acceptance number? See.
So, here, probability of acceptance number.
Yeah, sample. We need when you are doing a reliability sampling plan, we need the sample size and the acceptance number to decide the either to accept or reject condition. What about those values? You have given a real example. What about the table computations?
Yes, sir. Here,
For
using.
for different parametric values.
Yes, sir. Here,
Are you working?
yes, sir. Yes, sir.
Madam, sir is asking what about the sample size and acceptance number C for your study?
Acceptance number C
Yeah.
is 2, sir.
No, that's what. How you frame that and what is sample size is required?
So,
Any
sample
table will
size
be
is-
calculated or not? Sir is asking.
So, sample size is 6, and then using Python,
Okay.
and there is the cumulative density function.
Have you derived the table? Have you derived the table?
No, sir.
That's what sir asking. That is what sir asking. Have you
Yeah.
derived the table or
Sir,
not?
processing, sir.
So it is in pipeline, right?
Yes, sir.
Okay. Sir, they are working on that. I think so. They have fixed
Okay.
sample size
Okay.
with fixed example numbers. They have fixed there. But full the table derivative, they are working on it. I think so.
Okay. Nice. Yeah, it is a new area, na?
Yes,
they have
neutroscopic statistics is an
Yeah.
emerging area.
Yeah.
So many people are
emerging.
working on fuzzy theory.
Fuzzy and neutroscopic.
Neutroscopy. This other word we used to call.
Yeah.
But there is a good scope for the advanced technologies we can use there.
Yeah.
In neutroscopy studies. So I think recently I read one paper by that Aslam paper, I think so. Aslam have written recently on paper the neutroscopic statistics. So I think based on that she is working, I think so. So anyhow, thank you, Professor Gade sir, for your very simple and nice question. And any more questions for the speaker? Okay, if there is no question, so on behalf of the organizing committee member, I thank Dr. Jayalakshmi
Tn converges in distribution to normal 0, 1. With the above approximation, we obtain the 100 into 1 minus alpha percent confidence asymptotic Wald confidence interval for g of theta as g of Tn plus or minus z alpha by 2 into modulus of g dash of Tn into sigma of Tn. So this way we construct the asymptotic Wald confidence interval for g of theta. Using the above result and the delta method of construction of superefficient estimators, we can construct the SEE-based asymptotic confidence intervals. We note that in case of the event where theta n cap is closer to theta naught of an order closer than n power minus 1 by 4, if this event is occurring, then the SEE theta n tilde is just g of theta n cap, where g is the function considered under the delta method. We refer to an earlier equation wherein the SEE theta n tilde has been defined, and the equation 6 from which we get the asymptotic distribution of theta n tilde. So basically, these two are the equations 5, and the equation 6 is what I'm referring to. Proceeding in the same way as constructing the AEE-based asymptotic confidence interval, the SEE-based confidence interval is theta n tilde plus or minus z alpha by 2. Square root of, there are two terms involved. The first term is present when the event theta n cap minus theta naught, if that distance is closer to the order of n power minus 1 by 4. If that happens, then we get g dash of theta naught squared into I inverse of theta n tilde by n as the expression there. Whereas if the other event occurs, if theta n cap is not closer to theta naught to the order of n power minus 1 by 4, then we have just I inverse of theta n cap by n, which is just what we have got for the MLE, because theta n tilde simply coincides with the MLE when the event, the closeness between theta n cap and theta naught does not happen. Theta n tilde happens to be same as the theta n cap. We have used the notation K to denote the indicator function for the events, because we can use I as the indicator event, but then I is already reserved for the Fisher information, and therefore I'm using the notation K. Sometimes we can use the notation chi to denote the indicator functions. Some past research, I'm not giving an exhaustive collection, of course. There is a good collection of research papers on estimation of the Poisson. So I'm looking at the Poisson parameter estimation case here, estimation of the Poisson parameter covering theoretical and application aspects. We can refer to Glaser 1962 for minimum variance unbiased estimation of Poisson probabilities, and Simar 1976 for estimation of a compound Poisson process. There are interesting applications of inference for Poisson parameters. To mention one, Unser and Aden 1988 discussed maximum likelihood estimation of linear signal parameters for a Poisson process. Coming to the super efficient estimation idea, recently Durarajan, my guide, Dr. Durarajan, in 2012, he considered subscore and super efficient estimation in a paper. Now there are such developments and applications that have happened, but super efficient estimation of parameters, and specifically any methodical approach to construct SEEs, have not found place in the past developments. Now, a class of super efficient estimators for the Poisson parameter. Let x1 xn be ID Poisson with parameter lambda. We consider the function g on the parameter space as g of lambda equal to c into lambda by c raised to the power d for lambda greater than 0, where d is a known number, a fixed number in the open interval 0 to 1, and c is any point in the space of the parameter lambda. Clearly, we can see that g of c is equal to c, and absolute value of g dash of c is less than 1. In fact, modulus of g dash of c, you can see it is nothing but d, which is less than 1. Hence, according to our formulation, C can be chosen as a point of super efficiency, and a super efficient estimator can be constructed as follows, according to what we have given earlier in equation 6. lambda n tilde of d, because d can vary, we can choose any d we like, c into x bar by c power d, if x bar is closer to c to the order of n power minus 1 by 4, otherwise it is just the MLE itself. According to the foregoing theory, the above equation provides a class of super-efficient estimators for the parameter lambda with C as the chosen point of super-efficiency. We can vary D over the interval 0 to 1, and we can get a big class of super-efficient estimators, all with super-efficiency point C. In the sequel, I shall discuss a real-time application of the proposed super-efficient estimation, just as an example to demonstrate the use of super-efficient estimate. Application to estimate district-wise dowry deaths. The social institution of marriage has evolved over the centuries with many historical changes in India. Dowry deaths are evil occurrences forced upon married women who are murdered by their in-laws or are pushed to commit suicide. It is widely reported that incidence of dowry deaths has been showing an increasing trend over the years, with the price, not a good word, but with the price of bridegrooms shooting up due to scarcity of grooms in the marriage market. The National Crime Records Bureau reveals that after dowry deaths are reported, 93.7% of the accused are charge sheeted, but only 34.7% have been convicted. This paints a gloomy picture of women's safety. We refer to certain articles which discuss the reference system in North India, the dowry system in North India, which is very prevalent in North India, and also a paper by Edlund 2006 for a South Indian dowry debate. Motivation for using the Poisson law. With all its intensity and penetration in society, it is indeed a consoling truth that dowry deaths are still rare in our society. Thus, the occurrence of dowry deaths in a given geographical region, say a district, over a chosen unit of time can be viewed as governed by Poisson law. In the sequel, we wish to apply the ideas of estimating the Poisson parameter using the super-efficient estimation approach to estimate the monthly average number of dowry deaths per district across India reported for the census years 2001 and 2011. We also wish to compare the rates of occurrences in these 2 years using the appropriate confidence intervals. The data for the study are drawn from the following website. The total number of districts for which data are reported at district level across the states and union territories of India is 681 according to the administrative structure in 2001. In 2011, this number increased to 756 owing to bifurcations of several districts that were carried out in the intervening years. For 2011, we take the number as 681 itself by using the data at the composite district levels as per the 2001 structure in order to have a meaningful comparison. We intend to study the average count of dowry deaths per district per month of the years 2001 and 2011 by constructing 99% confidence intervals of these means by using the MLE, and 2 by using an appropriately chosen super efficient estimator with super efficiency point lambda equal to 1. I have discussed in general as a point C, but here we have taken the point C as 1. We consider the super efficient estimator lambda and tilde of D, where we choose D as 0.5. D can be any number between 0 and 1. We are taking 0.5, and the point of super efficiency is C is equal to 1. We note that the super efficiency point chosen for our super efficient estimator lambda and tilde 0.5 is 1, as the threshold of 1 death per district is considered to be an alarming value to be watched with concern and caution. MLE-based confidence interval. As we know, the 99% asymptotic confidence interval using the MLE of lambda is given by lambda cap plus or minus z alpha by 2 into square root of lambda cap by n, where alpha is taken to be 0.01 and we get 2.575, where MLE lambda cap is nothing but the observed mean number of dowry deaths per district per month. The SE-based confidence interval, as per the formulation which was presented earlier, using the supervision estimator lambda n tilde of 0.5 is given by lambda n tilde 0.5 plus or minus z alpha by 2 into square root of, there are two terms as I stated earlier, if x bar and 1, the superefficiency point 1. If they are close enough to the order of n power minus 1 by 4, then we get g dash of 1 squared into lambda n tilde 0.5 by n. Otherwise, it is simply lambda cap by n, and that is the second term. So it depends on what the nature of x bar happens to be, how close it happens to be to 1. That is, you can see g dash of 1 is nothing but 0.5. Actually, g dash of 1 is d, and we have taken d as 0.5. And lambda n tilde of 0.5 for the constructed estimator is lambda cap MLE power 0.5, x bar power 0.5 by n, plus the second term which involves x bar by n directly. From the available data, we compute the MLE x bar, the SEE lambda n tilde 0.5, and the corresponding 99% confidence interval separately for the 2001 and 2011 data as reported below. You can see the estimates and the condition check that is given there. For the year 2001, we note that the condition modulus x bar minus 1 less than or equal to n power minus 1 by 4 is not satisfied, as you can see from the first line corresponding to the year 2001. This condition is not satisfied, and by theory, the MLE and SE are therefore identical, and so are the confidence intervals based on these. The 99% confidence interval is centered at 0.8384, as you can see from there in the first row, which is the mean number of dowry deaths per district per month across India in 2001. For the year 2011, however, the condition mod x bar minus 1 less than or equal to n power minus 1 by 4 is satisfied, and the estimates from the MLE and SEE methods are different. You can see it is 1.0546. You can see in the second column under MLE column, and under the SEE column, you can see 1.0269. So these are the different estimates that we get by the MLE and the SEE method, and so are the corresponding confidence intervals. You can see the confidence intervals are different. It is found that the shorter width of the confidence interval based on SEE, you can check that the interval width is shorter compared to the width of the confidence interval based on the MLE, and it compares favorably with the MLE based confidence interval for the year 2011. Of course, for the year 2001, they are same. MLE and SEE based approaches give exactly same estimates. We note that for 2001, both methods give the same confidence interval, as we find from the 99% confidence intervals. The mean number of deaths per district per month is significantly less than 1. In fact, you can see the confidence interval which is lying between 0.812 and 0.864, and therefore the mean number of deaths per district per month happens to be significantly less than 1 in 2001. For the year 2011, while the MLE-based 99% confidence interval shows the mean number of deaths per district per month as having crossed and significantly exceeded 1. You can see the confidence interval given by the MLE in the last row, 1.02 to 1.08, which shows the death rate has actually increased beyond 1 significantly. However, the SEE-based confidence interval shows that the average has not significantly exceeded 1. You can see it is 0.998 to 1.055. At the same time, the SEE-based analysis shows that the average in 2011 was 1, while in 2001 it was significantly below 1. Relating the dowry deaths of 2011 with 2001 as base, the MLE-based analysis reports a 25.8% increase in the dowry death rate, whereas the SEE-based analysis reports a conservative estimate of 22.5% increase. In contrast with this, during 2001 to 2011, the total population in India recorded just a 16.4% increase from 1071.5 million to 1247.2 million. The dowry death rate has increased
Sir,
more
2
rapidly
minutes,
than
sir,
the
2 minutes
population.
only. 2 minutes
Yeah,
only.
I'm closing. This should set alarm bells ringing in the nation's conscience towards initiation of more proactive measures for preventing dowry deaths. And this is the last slide. Some comments about the SEE considered in this equation. It may be seen that when the MLE is close up to some threshold, up to the order of n power minus 1 by 4, close to the point of super efficiency C, the SEE essentially moves the estimate closer to C. Some investigation on how the class of SEs lambda and tilde D for variation D in the interval 0 to 1 performs, how the class of SEs performs vis-a-vis the MLE in small samples have been carried out in the PhD thesis of one of my students, Dr. K. Sivasakti, who completed his PhD in 2021. Some explorations on super efficient estimation in the multi-parameter context have also been done, and some results have been obtained but have not yet been published. The area of super efficient estimation is a classic one but has not yet been explored much. A few research papers have recently been published, co-authored with my scholar, but there is a good scope to work on this area. For instance, the estimation of the expected outcome variable in a Poisson GLM is an interesting area wherein super efficient estimation can be thought of to obtain closer estimates to the true values. And also investigation of SEs, uh, construction of SEs instead of MLEs for various parametric models is an open research area to work on. And that brings me to the end of my talk. And these are the references and all some very few references I have given. And these are the recent publications published by my research scholar, Dr. K. Sivasakti. I would like to thank my guide, Dr. Durarajan, who basically initiated me after his retirement, after many years, after me completing PhD under him. He gave me the idea of working on the super efficient estimation theory, and I am happy to have presented my research here. And thanks to Dr. Sivasakti for taking up this work as a part of his PhD thesis work. Thank you, one and all.
So now it is open for comments, questions, etc. Any question, please? So anyway, so I will ask one thing, Dr. William.
Yes, sir.
Are you ready? Can I ask now?
Yes, yes, sir, sure.
So in equation number 9, so you have in fact a class of super efficient estimators, right? So
Yes.
right. So could you take that slide up?
You want me to show the slide?
Anyway, so if you recall, then it is fine.
Yeah,
So
yeah,
in that,
yeah. Definitely. Yeah, I can recall it. Yeah, 1 second. I'll
in
share
that
the
slide-
screen. No problem. I can share the screen. Just a minute. Can you see the screen?
Yeah. Even in concluding remarks, it is there. So if we look at this, even concluding remarks, so you have the estimated lambda and hat is equal to something, and a condition is there that root of n is less than x bar minus c into less than or equal to n raised to 1 by 4. So is there any mathematical interpretation of this condition? Because it is less than n raised to 1 by 4.
I mean, it is a mathematical. Of course, it's a mathematical. What do you call maneuvering of mathematics, of course. But then the idea seems to be that whenever we have a point of super efficiency which is chosen conveniently, of course, there should be some reason of why we should choose a particular C as a point of super estimation, point of super efficiency. And if the MLE is closer to C to to the order of n power minus 1 by 4, then essentially what we are trying to do is we are trying to move the estimator closer to the super efficiency point C. So x bar will be now still becoming closer. The estimate, instead of x bar being the estimate, we will be getting a value which is still closer to C as the estimate for the parameter lambda. So this is the approach that is followed in all the models, including Poisson as well as other models, normal models, which we have studied in especially Dr. Sivasakti's thesis, where basically the difference between the MLE and the point of super efficiency is the main character of interest. And if that becomes closer than the order of n power minus 1 by 4, then we get a different estimate. Otherwise, it is just the MLE itself. And the mathematical theory proves that this particular estimator is having a better variance at the point of super efficiency compared to the asymptotic variance of MLE. So that is how the justification for the super efficient estimation approach follows.
So that's right. So, but in computations, I may have missed something, but this condition was written as less than or equal to n raised to minus 1 by 4. See, you
yeah, that's the root n. The root n should be avoided there. So modulus of x bar minus C is less than or equal to n power minus 1 by 4. So I have included a root n on the left hand side, and that is why it is coming out as n power 1 by 4.
Any other query? So anyway, so if there is nothing else someone wants to ask, so let us thank the speaker for a very interesting talk. So let us thank the speaker.
Thank you, sir. Thanks a lot. Let me once again thank Professor Satish Kumar for the wonderful opportunity. I'm really humbled to be present here in the presence of stalwarts like Narendra Kumar, KK Jose, and of course you, Professor Satish Kumar also. And I'm very happy that you have given me this opportunity. And I should thank my PhD scholar, Dr. Sivasakti, who was interested to take up this particular rare area of research. In fact, when we took up this thesis and when we wanted to go for examiners, we had a tough time in getting examiners for the thesis because we could not find people who were working on this area, and it was very difficult. It is a rare area indeed. I should acknowledge my guide, Dr. Durirajan's support and his motivation to me all along my life, my career. He has been my motivating force, and I thank Dr. Durirajan. I place on record my thanks to Dr. Durirajan here. Thank you so much, Professor Narendra Kumar, for the question and also for the nice words. Thank you once again. Thank you, Dr. Satish Kumar.
Thank you, Professor Martin, for your nice talk. Very clear.
Right. So now we move on to the second talk of the session. So I do see Professor Jose on the screen. Namaskar, namaskar. Welcome to the session.
Namaskar, sir. Namaskar, sir. I will just share my slide.
Just a minute. Let me first introduce you.
Okay.
Before I introduce you, sir, because it is good to see you first of all. Personally,
after 10 years.
Yes.
After some around 20 years.
Right. That's very.
While I was in Rajasthan.
So before I move further and introduce Professor Jose, so let me check the third speaker has joined or not so far. So otherwise, Professor Satish has to.
Yeah, he's here in the group, Professor.
Then it is fine.
Yeah, he's there.
Right. So now I introduce Professor KK Jose. So Professor Jose is presently working as Honorary Director, School of Mathematics and Statistics and School of Data Analytics at Mahatma Gandhi University, Kottayam. Professor Jose is an eminent academician who had rendered more than 42 years of meritorious service as a reputed principal, professor, and head of the department, teacher, researcher, and organizer. His areas of research include statistical modeling, stochastic processes, time series modeling, distribution theory, sampling theory, queuing theory, reliability analysis, multivariate analysis, and so many other fields. Dr. Jose has successfully guided over 25 research scholars in their PhD work and published more than 150 research papers in reputed national and international journals. In addition to that, he has authored 5 research-level books and successfully completed 6 research projects sponsored by the agencies like MOSPI, DST, UGC, etc. So he had been the convener of 5 DST, SERC, SERC schools and 4 DST undergraduate training camps at mathematics. He had been a member of SERC division of Kerala State Council for Science, Technology and Environment for monitoring research projects, as well as committee for state strategic plan of Department of Economics and Statistics, the Government of Kerala. Dr. Jose is an elected member of the prestigious International Statistical Institute, Netherlands, and a fellow of RSS, World Statistical Society, UK. He's also a member of various professional societies like ISPS, ISBA, Bernoulli Society, IMS, etc., KFC, etc. He had been invited speaker, resource person for more than 150, national and international conferences, workshops, etc. We welcome you, sir.
Thank you, sir.
So you have very rich credentials. Now I invite you to go ahead with your talk.
I will share. Very good evening to Professor Narinder Kumar, the chairperson, and Dr. Sadish Kumar, the organizer. So for giving this opportunity in this auspicious occasion of celebrating the National Statistics Day. So I will share my slide. I think it is coming.
Sir, you have 30 minutes and 5 minutes we will have for the discussion.
Okay, sir. So, greetings of the National Statistics Day, and my topic is actually on auto-regressive processes for financial modeling. And as far as auto-regressive processes are concerned, so what you can see is actually auto-regressive processes. It's actually a special case of time series modeling. So time series is a realization of a stochastic process. It is a sequence of, so the slide is not coming, I think. Okay. No, it is coming. Time series is a realization of a stochastic process. It's a sequence of chronologically arranged observed values of a process like atmospheric temperature, price of a commodity, sales, exchange rate of currencies, etc. So you will made a systematic study in 1927. So it is around a century that a rigorous study on time series models have been conducted. So Box and Jenkins in 1970 made the systematic study, and their classical book is actually regarded as the Bible of this time series modeling. And they have developed the Box-Jenkins models called the ARIMA models, as well as the ARMA models. So stationary situation is ARMA models. And certainly there have been various generalizations like this Subarau's generalization. So Subarau actually extended it to the nonlinear case actually. So in the nonlinear case, you are having a combination of auto-regressive part, the moving average part, and then you will be having the nonlinear part, that is actually a combination of a product of the process multiplied by the innovation x t minus I into epsilon t minus k. So with the addition of that last term, you are having a nonlinear process actually. So this is actually a generalization of the ARMA model, or it is denoted by BLPQRS, and if R equal to 0 and S equal to 0, if the last term is absent, it actually reduces to the ARMA PQ model. So various types of models are there actually. So now coming to the generalizations, what you can say on suggesting a model for a time series data. So different features such as simplicity, inference, parsimony, predictive power, archaic information criteria, etc. are to be considered. And based on that, you can develop good time series models actually. So Gaussianity, linearity, and stationarity were the basic assumptions of time series modeling till 1980s. And the need for non-Gaussian auto-regressive models have been long felt from the fact that many naturally occurring time series are actually non-Gaussian with Markovian dependent structure. So just like income data and such other situations, you are having this type of distributions or this type of dependence. So that is actually what actually lead us to the non-Gaussian situations. So now we will be coming to a very simple example, that is actually the exponential autoregressive structure. So before going to that, I will give a quick revision. That is, so the first or the pioneering work was actually by Gower and Lewis in 1980, which was a paper which appeared in the Journal of Applied Probability, introducing exponential autoregressive process. And in 1978 itself, actually Lawrence had presented a paper on these autoregressive models with exponential marginal distribution, then Laplace, gamma, and so on, mixed exponential marginals. So Laplace in 1981 revised the model given by Gower and Lewis in 1980 to deal with the problem of zero deficiency. Some defects were there, so that also was rectified by Lawrence in 1981. Subsequently, a large number of non-Gaussian time series models were introduced and studied by various authors actually. So this Brockwell's book is actually a good reference for them. Modeling of data in terms of, in the field of reliability, hydrology, etc., as well as from biological, socio-economic, and financial contexts, and actually necessitated this type of exponent, what you can say, non-Gaussian models. And coming to the structure, so of the AR1 model, so the AR1 structure is actually given by xn equal to rho xn minus 1 plus epsilon n. That is, xn depend on its own just previous immediately preceding value xn minus 1. So xn is equal to rho xn minus 1 plus epsilon n, where rho can take values from minus 1 to plus 1. So modulus of rho is less than 1. And here the problem is actually to find an innovation sequence epsilon n, which is a sequence of IID random variables called innovations. And what in most of the non-Gaussian time series models is actually we are constructing a model in such a way that, or we are developing an innovation sequence in such a way that the stationary marginal distribution is a given distribution. So in this case, exponential case, it is the exponential distribution with the parameter lambda. So that is actually the purpose. And for that, if you proceed, you can see that. So it actually leads to, so the exponential case, if you consider the characteristic function phi xt is lambda by lambda minus it, and that will lead us to phi epsilon t equal to lambda minus I rho t by lambda minus it, which you can rewrite in the form rho plus 1 minus rho into lambda by lambda minus it. This actually gives some insight to the autoregressive structure or the innovation structure. So the innovation epsilon n is having two components, that is 0 with the probability rho and an exponential random variable en with the probability 1 minus rho. So when I substitute in the process, xn is actually becoming rho xn minus 1 with the probability rho and rho xn minus 1 with the exponential random variable en with the probability 1 minus rho. So even though we have started with a linear model, it actually leads us to a non-linear model. That is actually what is happening here. And this actually is having a strong connection with what is called self-decomposability. So self-decomposability is actually something like this one. So in terms of characteristic function, you can say if for every rho in 0, 1, there exists a characteristic function phi p such that phi t is equal to phi x rho t into phi rho t. So in that case, this actually, so it has been proved that autoregressive structure of order 1 or AR1 process can be defined only if and only if the innovation is actually following this structure that is actually in the self-decomposable class of distributions. It is also called the Levy class also. And in 2005, Satish and Sandhya just modified and noted that AR1 model can also be defined in some restricted cases at least. And in that case, it need not be true for all rho in 0, 1, for some rho in. So in that case, they refer to the distributions or the class as semi-self-decomposable class. And semi-self-decomposability is actually something which actually developed by Japanese statisticians Majima and Ito in 1998. And for them, it is actually if for some 0 less than rho less than 1, there exists a characteristic function phi p such that phi t is equal to phi x rho t into phi rho t. That is for some rho in the range 0 to 1. So that is actually the advantage of this. And that is also possible. So we can go up to semi-self-decomposable classes. Now, another modification is actually due to Lawrence and Lewis in 1981. So here, Bondas in 1981 noted that first-order AR1 model can be defined only for self-decomposable random variables, but with Sadish and Sandhya's result, we can define AR1 models for some values of rho in the range 0 to 1, provided the distribution is in the semi-self-decomposable class. In the Lawrence and Lewis model, so Xn is actually having this structure E epsilon n with the probability alpha, and rho Xn minus 1 plus epsilon n with the probability 1 minus alpha. So here, this innovation is having a significant probability alpha, whereas rho Xn minus 1 plus En with the probability 1 minus alpha. That is the autoreduced structure exactly occurs only when only in a fraction of time. That is 1 minus alpha, that is the probability. But in some situations, this epsilon n is having some major or some significant probability. So just like some stock market catastrophes, or something like some huge rains for 1 or 2 days, or so some world war or some war takes place in some country. So with that, actually the stock markets, the situation, etc., changes significantly. That is actually the problem in such a situation. So in that case, you can have this NEAR1 model, and that is actually going to lead to something called random self-decomposability. So in that case, suppose you consider the model, then you can write phi x and t in terms of characteristic motion. It is actually phi x and t is equal to this one. Under stationarity, it becomes phi xt equal to phi epsilon t into alpha plus 1 minus alpha phi x rho t. And here you can see that if alpha is equal to 0, it is self-decomposability. So phi xt is equal to phi epsilon t into phi x rho t. And if alpha is equal to 1, then rho equal to 1, then it's actually leading to some other class that is called geometric infinite divisibility. So that is actually the modification. When alpha equal to 0, it reduces to self-decomposability. Otherwise, when rho equal to 1, it actually leads to something called geometric infinite divisibility. And geometric infinite divisibility is in this form. So it was actually Professor Arun Pillai who developed most of the theory in geometric infinite divisibility. So myself also developed this theory. So actually Xn, suppose Xn is equal to epsilon n with the probability alpha, and is equal to Xn minus 1 plus epsilon n with the probability 1 minus alpha. This is a modification of the celebrated random walk model in economics. So in the random walk model, Xn is equal to Xn minus 1 plus epsilon n. So here we are having Xn equal to epsilon n, two components, epsilon n with the probability alpha and Xn minus 1 plus epsilon n with the probability 1 minus alpha. In that case, the equation is actually given by, in terms of characteristic motion, it is actually phi xt is equal to phi epsilon t into alpha plus 1 minus alpha phi xt, given by this equation number 7. So this is the condition for geometric infinite divisibility, and that we will be obtaining as a special case of, say, our random self-decomposability. So now coming to further, we will be going to some illustrations actually. And geometric infinite divisibility, I will just give a formal definition. Geometric infinite divisibility is actually defined as in this way: a random variable x is said to be geometrically infinite divisible if x can be written as a geometric sum, that is a random sum, sigma I equal to 1 to nu p xi, where nu p is actually a geometric random variable. So probability nu p is equal to k is equal to p into 1 minus p raised to k minus 1, where this x and nu p are independent. And in terms of characteristic function, we will be getting the same expression we have seen. And if you proceed, so you will be getting the generalization itself, that is actually the random self-decomposability I have already defined. So that is actually, so this random self-decomposability actually connects all this self-decomposability as a special case, geometric infinite divisibility also as a special case. So that is actually the purpose of this. So all these are actually coming under the random self-decomposability situation. Now we will be coming to generalization. So that is actually some illustrations using some. So we are actually having a unified framework for Gaussian and non-Gaussian autoregressive models. As I already said, non-Gaussian autoregressive time series models have been from 1980s, but Gaussian, that was actually something separate. So in 2008, 2009, myself and my student in her very well established work, so we developed a unified framework for Gaussian and non-Gaussian time series modeling through the convolution of a Gaussian and non-Gaussian random variable. So it is a very simple idea, but it actually combines both the Gaussian as well as non-Gaussian. So this procedure is illustrated through the convolution of, so we are considering normal and generalized Laplace. So normal and Laplace or normal and generalized Laplace. And consider the convolution x equal to z plus y, where z follows normal distribution with the mean mu and variance sigma square, and y is an independent self-decomposable random variable. So in that case, so what you can observe is actually this will lead to a combination of both. So if you write characteristic function phi xt equal to phi z into phi yt, and if you apply this in the autoregressive structure of order 1, that is xn equal to axn minus 1 plus epsilon n, you will be getting something like this. Phi epsilon t is equal to phi xt by phi xat. So which will give you phi z prime t into phi ut, where z prime, that is another normal random variable, normal with mean mu into 1 minus a and variance as sigma square into 1 minus a square, and this z, this un, that is any self-decomposable random variable. So that we will be getting the innovation structure as epsilon n equal to zn plus un, where zn and un are independently distributed as normal and an appropriate non-normal distribution. The only condition is it should be a self-decomposable distribution. So self-decomposability is actually needed along with this normality. Now, some such distribution is actually, one is actually this, so I have already considered it. I will come to the next slide, so which will lead to let me write. So Gaussian SEM is self-decomposable class, and we'll be having the autoregressive structure, generalized normal Laplace distribution. So this generalized normal Laplace distribution is actually a generalization of this normal as well as Laplace, a combination of normal plus Laplace whole raised to delta. So when delta equal to 1, it is just a convolution of normal and Laplace. Otherwise, it is a convolution of normal and gamma. So that is actually, so this is known as the generalized normal Laplace random variable. So the distribution structure, etc. This was actually introduced by Reed and Jorgensen in 2004, and the structure of the distribution is little bit difficult to say. Anyway, this is actually of the form. You can see the structure as something like a gamma difference multiplied by a normal distribution. So that is actually the structure of this, and that is actually giving the model. So here you can write it as x is distributed as z plus gamma 1 minus gamma 2, where gamma 1, g1 and g2 are independent random variables following some gamma distribution with parameters say alpha and beta, you can say. So that is actually the advantage of this. And this random variables or this type of distributions are also known as generalized Laplace distribution. Say very details in detail, it was studied by Mathai and so on. So that way we can have the distribution also. So we will be coming to the distribution structure and the autoregressive model. So in the autoregressive structure, so it actually gives to phi xt by phi xat, which will lead to this form phi epsilon t equal to, which will reduce to a simple structure. So something, so this is a alpha minus iat by alpha minus it, you can write as a plus 1 minus a into alpha by alpha minus it raised to delta. It is not just an exponential one, it is actually having a component at 0 also. So how to develop this term? So for that actually we can have something like a short noise representation. G1 n star is equal to sigma r equal to 1 to 1 a raised to ur into yr, where yr is a short noise process and exponential shorts, and UR is a sequence of independent uniform random variables actually. When N is a Poisson random variable with mean delta into log 1 by A. So that is actually the advantage. This short noise representation will give you the generation. So this will lead to the generation of the random variable also. So that is actually the advantage of this representation, and we will be coming to further results. So the innovation structure we have, then we'll be having the model. So the model you can write as, so epsilon n is equal to Zn plus G1n minus G2n, or G1n star minus G2n, where G1n star and G2n star are independent delta fold convolutions of exponentially tailed random variables. Exponential tail means we are having a zero component in the beginning. So we have considered this case, and you can write this as alpha minus IAT by alpha minus IT, etc. You can write as P1 plus P2 alpha by alpha minus IT plus P3 beta by beta plus IT. So all this you can write in terms of exponential and exponential convolutions, you can say, with a zero component also. So that actually makes the generation of the random variables further simple. So we will be proceeding, and one more representation is possible. So this eta n equal to epsilon n can be regarded as a delta fold convolution of the form eta n equal to Zn with the probability P1, Zn plus E1n with the probability P2, Zn minus E2n with the probability P3, where E1n and E2n are independent identically distributed as exponential with the means 1 by alpha and 1 by beta and so on. So this type of representation is more advantageous and more convenient for generation of the random variables. Then our usual say the distributions we can write, then it's just a distributional form. Then we'll be having the results. So you can write, say, the characterization of the innovation can be obtained in the form phi epsilon t is equal to P1 phi ZT into P2 phi ZT into phi epsilon 1t plus P3 phi ZT into phi epsilon 2 minus t whole raised to delta. And that actually gives the result. So the theorem AR1 process xn equal to AXN minus 1 plus epsilon n is strictly stationary Markovian with the generalized normal Laplace marginal distribution if and only if epsilon n are IID as defined by this characteristic function. So that is actually the main result. And then we can have the asymptotic case also. Asymptotic case means even if you are having x naught to be distributed arbitrarily, so that means you start with any arbitrary one. So as far as this structure is concerned, then the process is asymptotically Markovian with the GNL distribution. So the proof is also there. So we can go to the next slide. That is actually the autocorrelation structure. As far as the autocorrelation structure is concerned, we'll come to the autocorrelation structure. Autocorrelation structure is concerned, it is having correlation xn minus r equal to a raised to r. So that is actually the usual structure of autocorrelation for any AR1 process. So that is maintained here, even though we are having somewhat complicated expression or complicated structure for the innovations, we are having the autocorrelation structure, which is very important in the model identification, etc. So the same structure, a raised to r, is there. Then the mean and variance you can very easily obtain. That is actually the advantage. It is a finite quantity also. Expectation of epsilon n is equal to 1 minus a delta into nu plus 1 by alpha minus 1 by beta. The variance is also possible. Higher order cumulants also can be computed very easily. So all these are actually possible. So that is actually the advantage of this. So mean and variance we can have. We can proceed to some more things actually. Mean and variance. Then so that is actually something like the sum distribution of sum. So just like in the exponent in the Poisson situations, we are having something like waiting time distribution. So this time, so this is actually something of that form. So how much time? So that is the distribution that also you can obtain. That is important in the case of time reversibility, etc. So then we are having regression and variance. Regression also we can obtain very easily. Expectation of xn given xn minus 1 is equal to ax plus 1 minus a into delta into, that is linear. Whereas the conditional variance is also linear. So that is actually another advantage with this model. Then we'll be having regression and variance. Then we can further go to the estimation of the parameters. The parameters can be estimated in terms of cumulants. That is actually the advantage. The the value A is actually nothing but the correlation, the first order correlation that you can obtain from the observations, from the data. The other parameters can be easily estimated by solving the equations obtained using 6 sample cumulants. So if you consider the sample cumulants, then you can obtain, similar to method of moments, you can obtain the estimates of the parameters. And they are asymptotically consistent also. So estimation of parameters in the special case when alpha and beta are equal, that is a symmetric Laplace situation is there, then we'll be getting further more closed expressions. So that is actually helpful. So that way you can obtain the estimates of the parameters of the model. Then as far as the sample path, simulated sample path is concerned, it is having some modifications or something like a random motion we will be having. Okay. Then we can obtain the generation. So if you want to generate the GNN lab, that is generalized normal Laplace, whatever is one process, you can make use of this algorithm. The algorithm is also given. And in a similar manner, you can proceed and you can think of the generation in another form. So if the delta is actually something like an integer, then it is very easy. Then we'll be having short noise representation that also we can utilize here. Then we'll be having further higher order processes also can be very easily developed. So xn is equal to a1 xn minus 1 plus epsilon n with the probability p1, and a2 xn minus 2 plus epsilon n with the probability p2, and so on ak xn minus k plus epsilon n with the probability pk. So provided p1 plus p2 plus pk equal to 1, and all pi's are in between 0 and 1. So you can develop that way also. Okay, sir. I will proceed.
Sir, 5 minutes more, please.
Okay, sir. No problem. Then we can have some ARMA structure also. If you are having xn equal to a xn minus 1 plus epsilon n plus b epsilon n minus 1. That is, it depends on the innovation epsilon n and epsilon n minus 1. That is actually the ARMA 1-1 structure. Then also it is very easy to develop the innovation structure. Then one more modification is actually even moving average structure. So basically in most of the cases, moving average structure is regarded as the most elementary. That is also possible with this model or with these innovations. Then we can generalize that to semi-Laplace, semi-alpha Laplace situations also. So the same thing, semi-alpha Laplace distribution is having some structure 1 by 1. The characteristic motion is 1 by 1 plus phi t raised to p. So if phi t is equal to t square, you will be getting the Laplace situation. Otherwise, it is going to be something like modulus of t raised to alpha. Then you will be getting the alpha Laplace distribution and a general structure of the form phi t equal to a into phi bt. That will lead to the alpha Laplace, semi-alpha Laplace structure. So these have been actually studied and developed by our Professor R.N. Pillai. And further generalizations are also possible. And we can have innovation structure very easily. The same structure will maintain Zn plus Un. That is also possible. So you can have the same structure. Then this actually leads to a class of distributions. So generalized normal alpha Laplace, special case is alpha Laplace, special case is generalized Laplace, then generalized normal Laplace distribution. All these are actually special cases. And we have these remarks, assumption of Gaussianity. That was actually basic one. So we have actually combined both normal and Laplace, or this actually leads to something like normal Laplace and generalized normal Laplace, and further extensions have been done. Then one more thing, so just like the log normal distribution, we can consider log Laplace distribution also in this case. That is, logarithm of the random variable follows a Laplace distribution. That is also considered. So that also is actually possible. Then we'll be having the log Laplace distribution and its properties. Properties are well-known properties. So that in that case also, we can have the process or the distribution. And in that case, the modification is actually, we are going to consider a further modification, that is actually the what you can say, the so it is actually product autoregression. So product autoregression is actually of this form. So yn is equal to yn minus 1 raised to alpha into epsilon n. So in that case, actually, if you take logarithms, it actually becomes additive. So logarithm of y alpha will be equal to alpha logarithm of yn minus 1 plus logarithm of epsilon n. So with this logarithmic transformation, it actually led to a simple additive model itself. So there is not much further theory is needed actually. So with this logarithmic transformation, we can have the same structure. So that is actually what is actually observed here. So coming to some modeling with the financial models. So I will come to that.
So, sir, 2 minutes.
Oh, okay, sir. Okay, so you can have a special case that is actually the Laplace case, and in that the gamma different generalized Laplace case, and that will actually lead to the distribution, then the data, then comes the estimation of the parameters. We can make use of conditional least squares curve method or the method of moments also, the generalized method of moments, and that will actually lead to the solutions. And so these have been successfully used, and we will be getting the solutions. There we can obtain the estimates, then we can we can fit the model, and that is actually going to be something like something symmetric actually. So it is not normal, it is actually going to be normal Laplace. Another is actually, so the parameters have been estimated and we have obtained all this. And then another is actually some inflation modeling. So Anderson has proved that this normal Laplace model is actually more suitable than, he's actually one of the best normal Laplace distribution is one of the best distributions which you can use for modeling inflation. So he actually considers this, applies this to some data on consumer price index of Switzerland, and he compares with the various distributions, and he finds that this normal Laplace model, so developed by myself and my student, is actually more suitable than almost all other models. So here are the statistics, the computations are actually here. So this actually concludes my talk. So our references are also available. Okay, sir. So these are the references. Kosubowski, myself, Keke Jos and Lishamor, and so on. Okay, sir. Thank you.
Thank you, Professor Jose. So now we have time for a quick 2-3 questions, please, because we are running short of time.
Okay. Nobody is asking questions.
So the estimators of the parameters which you obtain,
okay.
So they are explicitly obtained, or some packages being used like Mathematica and all that?
No. So we can make use of R programs actually. So this have been newly developed actually. So we have been using R programs actually.
So some programs are being made.
Oh, okay. R programs are needed actually.
Right. Anyway,
so they are consistent also. Some simulation studies we have conducted, and as the sample size increases, they converge to the actual value.
Anyway, so thank you so much, Professor Jose, for a very interesting presentation. So let us thank the speaker.
So thank you, Professor Narendra Kumar. So I have been meeting him, or actually we are seeing you after some 9 years. So I was there in 2015 at Central University of Rajasthan. Thank you very much.
Thank you.
Okay.
Thank you, sir.
Thank you.
So now we move on to the third speaker of the day. So he's already there. So we have among us Professor Srinivas Rao. So welcome you, sir, to this technical session. So
thank you, sir.
Thank you. So let me introduce you. So Professor Rao, Professor Srinivas Rao is presently working as a Professor of Statistics at Department of Mathematics and Statistics, the University of Dodoma, Tanzania. Professor Rao has more than 190 publications in different peer-reviewed, well-reputed national and international journals. including the Journal of Applied Statistics, International Journal of Advanced Manufacturer
പോയില്ല അത് പോയോ
IEEE Communication Statistics Theory and
അപ്പൊ പോയി
Mathematics,
അവർ
Communication Statistics.
പെട്ടെന്ന് പോയാ അവർ മിണ്ടാതെ പോയി
So please mute the mic, please. Journal of Testing and Evaluation, Arabian Journal for Science and Engineering, International Journal of Quality and Reliability, and many more. His papers have been cited more than 2 to 6, 7 times with H index of 24 and I index of 64. So Professor Rao is a reviewer of more than 60 well-reputed international journals. So more so, he's the author of 4 books or book chapters published in elsewhere, Springer Nature and Taylor and Francis. His research interests include statistical inference, statistical process control, applied statistics, acceptance sampling plans, reliability estimation, etc. He got World Scientist recognition in AD Scientific Index 2024. So he also got the first rank among the faculty members at the University of Dodoma, Tanzania. So he also received the president of Neurosophic Science International Society. He has been the president of that society of Tanzania, which is commonly called as NSIA branch, right? So welcome you, sir, to this session. So now you can please start your talk. So you will have 35 minutes for the 30 minutes for the presentation and 5 minutes for the discussion and all that. So please go ahead with you.
Okay. Thank you very much, Professor Narendra Kumar, sir, for your nice words about me. And I would like to thank the Professor Satish Kumar, sir, for inviting me to present my work in this conference webinar. Let me share my talk. Is it visible, sir?
Yes, it is visible. Please go ahead.
Shall I proceed? Yeah. Today's my talk is on neurosophic transmuted Rayleigh distribution for modeling the wastewater treatment. One minute. The framework of the study is the scope of the study, introduction, neurosophic transmuted Rayleigh distribution, introduction, statistical characteristics of the proposed distribution, parametric estimations, performance of the parameters using the simulation study, modeling the wastewater treatment data, and finally the conclusions and references. The scope of the study is the neurosophic transmuted Rayleigh distribution is examined in this work. We present an extensive neurosophic characteristics of the NTR distribution, the maximum likelihood estimation strategy, which is based on the neurosophic environment, is used to estimate the neurosophic parameters. The performance of these neurosophic estimators in terms of their neurosophic bias and neurosophic mean square errors of the parameters have been compared using the Monte Carlo simulation study. Wastewater treatment data is used to demonstrate the utility of the proposed NTR distribution for uncertainty data modeling. The proposed NTR model is compared with some recently proposed neurosophic distributions. We know that in many applicability domains, like in engineering, finance, healthcare, modeling, and assessing the longevity of the data is a crucial data. Numerous lifespan distributions have been used to model this kind of data. The quality of procedures used in the statistical study is heavily dependent on the underlying probability models or the distributions. Thus, a significant deal of effort has been put into develop a large classes of traditional probability distributions and associated statistical methods. However, there are still a great deal of important problems where the real data does not fit into any of the traditional probability distributional models. We offer a unique generalization of the transmuted Rayleigh distribution in this article named as the transmuted neutrophobic transmuted Rayleigh distribution. The Rayleigh distribution is regarded as one of the most practical life distribution. It is used in many fields, including biology, agriculture, medical, and other sciences. This model is used in analysis of wind spread data also. The Rayleigh model has a significant effect on quality of the methods employed in the statistical analysis. With a shape parameter 2, this distribution is the particular case of the two-parameter Weibull distribution. Rayleigh distribution was introduced and studied by the many others from the Rayleigh 1980 to still there are many others studied on Rayleigh distribution. Its PDF is well-known function in the equation 1 and the CDF is given in equation 2. Merovici 2013 generalized the Rayleigh distribution and he named it as a transmuted Rayleigh distribution. Dev et al. 2017 discussed the statistical properties and different methods of estimations of transmuted Rayleigh distribution. The transmuted inverse Rayleigh distribution is developed and features are discussed by the Ahmad et al. 2014. Recently, many others have studied this type of new transmuted Rayleigh distributions. The structure of the transmuted distributions in a quadratic nature is its CDF is expressed as 1 minus alpha times of f of x minus alpha times of distribution CDF function power 2. And its CDF can be obtained as f of small f of x times 1 plus alpha minus 2 alpha times of CDF of the base function. Here, capital F of x and small f of x, we call it as CDF and PDFs of the baseline distributions, whereas capital GX and small gx are the CDF and PDF of the transmuted distribution. It is clear that when alpha is equal to 0, the transmuted distribution becomes a baseline distribution. The transmuted, based on these expressions, from the Rayleigh distribution, we can obtain the transmuted Rayleigh distribution CDF as the equation 3, and its probability density function can be obtained as an equation 4. Here, beta is the scale parameter and alpha is the shape parameter, or you can also call it as transmuted variable. Here also, when alpha is equal to 0, this transmuted Rayleigh distribution becomes a Rayleigh distribution. Now we want to introduce a new domain of the study called as neutrophobic distributions. Actually, this neutrophobic theory was first introduced by the Samrandachi in 1998, and later on, they extended this study by different authors. The new school of thinking of nutrosophic theory is an extension of the fuzzy logics or fuzzy sets. So one can refer the more details from these others articles. Additionally, in Samrochi in 2014, investigated the nutrosophic statistics, which is an extension of the classical statistics that deals with the ambiguous or uncertainty data and related to the statistical probability distributions. And he named it as nutrosophic statistics, which is an extension of interval statistics that also examines the fuzzy interval sets. When data is known or deterministic, nutrosophic statistics become a classical statistics. As most of the real world application data sets are ambiguous, undeterministic, unclear, partially unknown, or incomplete. In these situations, it is preferable to use nutrosophic statistics procedures. So more details can be obtained from these others. The purpose of this work is describe the theory of nutrosophic probability distribution, named as transmitted Rayleigh distribution. This is also used in the quality control and reliability studies in a classical statistics, which inspires me to investigate the transmitted Rayleigh distribution in a nutrosophic environment, especially for the application of the public health. This work aims to develop a new nutrosophic transmitted Rayleigh distribution for the application of wastewater treatment, particularly in the context of where the mishandling could have a negative health effects in the human being. Because poor or untreated wastewater treatment can result in an issue that influence the other areas of environment. Wastewater treatment is an essential procedure in any industry. More recently, CASF 2023 used the wastewater treatment data with the environment of nutrosophic framework. Hence, we want to use the same data for our study also. In recent years, a nutrosophic probability distributions have been attracted by some others. For more details, one can refer the Samrochi in 2019 paper. They started studying the nutrosophic Weibull distribution. Later on, some others have studied nutrosophic generalized exponential distribution, nutrosophic Pareto distribution, nutrosophic exponential distribution, and nutrosophic Kumaraswamy distribution. Like that, they have studied different distributions. A new model is being developed to initiate the nutrosophic adoption of the transmitted Rayleigh distribution. This kind of method is capable to resolve the real-world practical issues when dealing with the indeterminate data in either a univariate or a multivariate scenario, especially when the data displayed interval statistics. About the interval statistics, so Samrochi has given a book in 2022. He discussed about how international interval statistics only handle the indeterminacy that can be represented by intervals, whereas nutrosophic statistics deals with all kinds of indeterminacy. Additionally, he made a point that interval statistics is a special case of nutrosophic statistics. So the remaining paper we'll explain one by one. So it is the introduction of the neutrophobic transmitted rally distribution. Aslam and Khan in 2019 conducted a thorough study on notation of neutrophobic statistics. Actually, it was suggested by the Samrochi in 2014. These researchers suggested that a neutrophobic variable can be written as T suffix n is equal to TL plus IN times TU. Here, IN is a indeterminacy factor, whereas TL and TU are the lower and upper values. Here we introduce the parameters for this NTR distribution. The scale parameter is Bn. It is an interval value BL to BU, and neutrophobic parametric value alpha n, which belongs to alpha L and alpha U. Here, TL, BL, and alpha L are the lower values, whereas TU, BU, and alpha U are the upper values. So let me introduce the neutrophobic probability density function of the NTR distribution as given in the equation 5, and its corresponding cumulative distribution function is given in the equation 6. So once, if you want to know the nature of the any distribution, we have to know the by drawing a probability density function of the distribution, even in a classical environment. Now, in neutrophobic environment, if you take your beta value, that is the scale value is 0.9 and the upper value is 1.1, alpha n is, so you know that in transmuted, alpha is in between -1 and +1. That's why we have taken alpha n is -0.2 to 1. So its nature of the distribution is like this way. And here, the nature of the distribution for another parametric values. And third is for the different other parametric values. It shows that it is gradually increasing and then gradually decreasing. So it could understand that it is influencing the both parameters beta and alpha. And its CDF curves are given for different values of the parametric values. So for our understanding, when alpha n is increases, the dispersion of unimodal neutrophobic distribution decreases. So it appeared from the figure 1. And in statistical properties of any distribution, another property is a neutrophobic reliability function. It can be obtained as in the equation 7. Its graphical nature is given in the next figure. And the neutrophobic hazard function is given in the equation 8. So from this expression, upon finding the first derivatives and second derivatives, we could understand that the nature of this distribution is IFR model. And the survival function of the NTR distribution is given. So it is in the same nature, gradually decreasing for different values of the variable. So other statistical properties to obtain the moments of the distribution, first we have to obtain the Sth moment about the origin, so which can be obtained as this formula. The proof of this result, this is a well-known result, whereas here we are expressing an interval neutrophobic statistics. So upon substituting S is equal to 1, 2, 3, and 4 in the equation 6, we can obtain the first four raw moments. The first moment is nothing but the mean of the neutrophobic mean of the entire distribution, and it is equation 11. And the second moment, third and fourth raw moments can be obtained in this manner. So we can also find the neutrophobic variance, and it is a well-known formula, and final result is given in the equation 12. We have also obtained the neutrophobic coefficient of variation, so that is given in equation 13. So we have given a mean variance coefficient of variation for different parametric combinations of neutrophobic parametric combinations, which are displayed in the table 1. From these results, we could understand that, so for example, if this alpha n is decreasing here, so when alpha n is decreasing, our mean value is decreases. Similarly, the variance is also decreases, and coefficient of variation is increasing. It could understand that the transmitted parameter alpha n is decreases, the mean value is decreasing, and variance value is decreasing. Sorry. Similarly, when beta value is decreasing, like this first row and second row, neutrophobic mean value is increasing, and variance is decreasing. Similarly, the neutrophobic coefficient of variation is also decreasing. So the remaining results also we can discuss in this manner. So when alpha n decreases, the neutrophobic mean and the neutrophobic variance values are increases, and when beta n value is fixed. Also, when alpha n is fixed, neutrophobic mean and neutrophobic variance values are increasing when beta n value is increases. So other important characteristics of the distribution is moment generating function. It can be obtained in this manner. So it is a big expression in terms of summations and gamma function, and it can be proved like this manner. It is a common formula. And similarly, characteristic function also could be obtained by using this formula. And next is the quantile function. The quantile function is very useful for generation of the random numbers and also to conduct the Monte Carlo simulation. So here, the quantile function can be obtained by Qn of P is equal to G inverse of P, which is not in a closed form. So therefore, it is a nonlinear equation which can be the quantile function can be obtained on solving this nonlinear equation 16. If you substitute P is equal to 0.5, we can get the median of the entire distribution. So based on this quantile function, we can obtain the skewness and kurtosis. So the skewness and kurtosis based on the formula suggested by the Galton 1983 and the Morse 1988. The skewness formula is given in the equation 17, and the kurtosis formulas are given in 18. So these are based on the octiles. So these formulas we can obtain. So similarly, the table 2 is displayed as the median, neutrophobic median, neutrophobic first quartile, and neutrophobic third quartile, neutrophobic interquartile range, and a neutrophobic skewness.
5 minutes more, please.
Okay, sir. Thank you, sir. And then which are displayed in the equation in the table 2. From these results, we can conclude that when alpha n is decreases, the kurtosis and skewness values are decreases for a fixed value of beta n, and also for a fixed value of alpha n, the median interquartile range are also increases as beta n increases. So for the beta n is not influencing on skewness and kurtosis because the beta n is the scale parameter. Next part of the study is parametric estimation. So here we applied the maximum likelihood estimation to estimate the parameters. The likelihood equation could be obtained as equation 19, and the log likelihood equation is obtained in the equation 20. So to obtain the MLEs of this, we have to differentiate with respect to the beta n and alpha n, which are given in the equation 21 and 22. So on solving these two equations in two unknowns, we will get the MLEs of the alpha n and beta n as alpha n hat and beta n hat, where alpha n and beta n are the interval values. The performance of the parameters can be studied by using the simulation study. So here we have generated the 10,000 samples of sizes n is equal to 20, 20, 30, and so on, 300 from based on the nutrosophic parametric values. And we have computed the average mean square error and the average nutrosophic average bias, which are estimated for different combination of the parametric values, which are displayed in the tables 3 to 6 for different combinations of the parameters. So these are the results from the simulation: nutrosophic average bias and the nutrosophic mean square error. So these are given in the table 6. From these results, we could conclude that nutrosophic bias and the nutrosophic mean square error decline with an increasing of the sample size. That is a natural phenomenon for any simulation study. Moreover, NAB and NMSE increases for all sample sizes when the nutrosophic scale parameter increases for a constant alpha n. Whereas in the reverse, for a fixed beta n, these values are also increases when alpha n is increases. So therefore, in a simulation study, the parameters are influencing in the estimation of the bias and MSCs. And last part of the study is modeling the wastewater treatment data. So this data, some extent I have explained in the introduction. Here we have considered the two parameters. They are biological oxygen demand and the chemical oxygen demand are the two crucial factors in the water treatment. So that's why we have considered here those two parameters. Whereas BOD indicates that the amount that can be oxidized biologically, and COD counts the amount of organic pollutants that can be removed chemically. These two are important for any water treatment. It was studied by Nagraha et al. 2017. It is important to note that there are varying quality standards for these two variables, and it is inevitable that for all samples will be able to receive the exact measurements, which was studied by the Bhattacharjee in 2022.
Sir, 1 minute, please.
Okay, sir. So these two nutrosophic variables are given in the BOD values are given, and COD values are given here, and these we compared with the different distributions like neutrophobic variable distribution, exponential distribution, generalized exponential distribution that I was studied previous, and neutrophobic gamma distribution and Rayleigh distributions, and we have computed the log likelihood value and AIC, BIC, and K statistic values. So which are displayed in the tables. So this is the descriptive statistics, and whereas these are the parametric estimators for different distributions. And we also compared for the quality of BOD data. From this data, we could understand that our model shows the smaller -2 log likelihood AIC, BIC values and W star and A star. Also, p-value is the maximum as compared with the other models, and our AIC, BIC values are smaller as compared with the other models. Therefore, for water treatment data, our model is better performing than to the other existing models. Similarly, we did for the neutrophobic estimates for COD data also. For this COD data, also it shows that our model is better performing than to the other existing neutrophobic distributions like Rayleigh, generalized exponential, variable distribution, exponential, and gamma distributions. So our final conclusion is, so the proposed neutrophobic distribution is useful for the environmental research and public health studies. So we can use this type of studies for any uncertainty data are occurred in the any practical applications. So therefore, we can suggest the government can monitor the effective industrial wastewater and establish the guidelines for the quality of wastewater from the industries by using the suggested NTR model. So we can also extend this work for the quality control and sampling plans also. So these are the some references. Thank you very much, Professor Narendra Kumar sir.
Any question, any suggestion, please?
I have a question. How do you collect data for this, and how reliable is the data? How clean is it?
This data we have borrowed from the published work.
Is it data from Indian conditions or some other places?
It is not Indian conditions, sir.
Then how can you expect government India to listen to that?
No.
Listen to your recommendations.
Because it is related to the water treatment, wastewater treatment.
Can be different.
Yeah, maybe situations are different, provided that if that such type of indeterminacy data is available and it is fitted to this type of models. It is a common phenomenon when you are taking a certain distribution, certain data, those data should be follows to a particular distribution, then only it is advisable.
Thank you.
Am I clear, sir?
No, but yeah, you are clear, but I'm not convinced. That's okay. Thanks.
Yes, sir.
Anyway, any other question, please? So if there is no other question, let us thank the speaker for the interesting talk.
Thank you very much, sir. Thank you very much, Professor Narendra Kumar sir and the Professor Satish Kumar sir for inviting me to share my research work in this conference. Thank you very much.
Right. So we are done with all the three talks in this session by Professor William, Professor K.K. Jose, and Professor Srinivasa Rao. So I thank all of them for presenting their talks and benefiting all of us and sharing their work at this platform. Thank you being with us in this particular session. Now it's over to Professor Satish Kumar.
Okay, sir.
Thank you, Professor Narendra Kumar, for chairing this session. And thanks to the speakers of the session.
Thank you very much, sir.
Yeah,
Thank you very much.
Professor Martin, Professor Jose, and Professor Gede. Thank you all.
Thank you, sir. Thank you.
I also see Professor Kaul here. Namaskar, sir. Namaskar.
Namaskar, sir. I said namaskar, but my microphone was mute when I said that. Very nice to see you, Narendra Kumarji.
Thank you so much.
Now everyone are waiting for next session.
We are all waiting for his talk.
Yeah.
Oh, thank you, so kind, very kind.
Namaste, Joshi, sir. Professor Joshi. Professor Joshi.
Yeah, he's there in the group. Yeah.
Thank you, sir. Thank you.
Yes. Yes.
We have some more 5 minutes more. 5 minutes. Let us 5 to 6 minutes. Yeah. Let us wait for that time. 5 to 6 minutes. Thereafter, move to this next session.
മുച്ചനെ ഞാൻ വിളിക്കുന്നില്ല വരുമോ ഇതിന് ഈ യൂണിവേഴ്സിറ്റി പോകണം ഇതിന് ഞാൻ രാവിലെ 7 മണിക്ക് പോക്കോളാം പരിപാടി ഇവിടേക്ക് ആരെങ്കിലും വില തരാന്ന് പറഞ്ഞാൽ ഇവിടെ കൊടുത്ത് കാശ് പഠിച്ചാൽ പോരെ ശബ്ദം പഠിച്ചു എന്നൊക്കെ ആൾക്കാർ കിട്ടാൻ കൂടുതലാണ് പാപ്പു പണ്ടിങ്ങനെയാണ് എല്ലാ അമ്മമാര് പറ്റിയിരിക്കാനുള്ള അമ്പാനിക്കാരുള്ള വിട്ടേച്ച് പോവാ
So not many people join. Sumesh Kumarji, namaskar.
Namaste, sir. How are you?
How are you? Where are you now? Kharagpur? Kharagpur, right?
Yeah, I'm in Kharagpur. Yes.
How are you? I haven't seen you for a long time.
Yeah, fine. I'm fine. Yeah. आप अभी कहाँ हैं? US में हैं?
Yeah, Michigan.
Yeah, Michigan. Okay.
It's Lansing.
I think Vellai Swami is going to Santa Barbara. He mentioned.
Right.
So you are continuing in the university, no?
No, I have retired, but I do continue my research, and they have given me office and all that. But other than that, I don't teach.
So some designation like emeritus or something?
Yeah, emeritus. that qualifies for some secretary support and office and all that is there,
Okay.
but no money, no travel money, no
Okay.
travel money.
Yeah, you can use the office and do some work. Yeah.
Right. And I can still use the name of the university. In return, they get whatever I publish under their name.
Yeah. Yeah, I think I saw you last in, Trivandrum conference, no? In physical mode.
Trivandrum, but now Trivandrum become digital, so it's all by virtual. So I've been telling Satish Kumarji to have in-house meeting. Trivandrum is always a great place to visit.
We can conduct conference in the December via hybrid mode. You can.
Yeah, but you have to find some money for me to travel.
I think IISA is doing.
I'll come no matter what anyway.
I think IISA is doing in I think December end.
They are doing in Bangalore.
No, it is in Cochin.
Cochin, sorry. Last was in Bangalore.
Yeah.
This was in Cochin.
Yeah.
And right now, they just finished this meeting of International Society of Non-Parametric Statistics in Spain, in Portugal. There was a big
Parvati?
about.
Yeah. Parvati?
Pardon me? Huh?
Yeah, let us start the session because it is time now, 6.
Sure. I think we can.
Welcome to us. Parvati?
Yes, sir.
Raji, okay, Raji. You please introduce the chair and help the chair to run the session next month.
Okay.
Yeah, please. We are
Good evening.
for Professor's talk. Please. Yeah, please.
Good evening, all. We are moving on to the 12th technical session of WSTA 2024, which is a keynote address that shall be chaired by Dr. Somesh Kumar. Dr. Somesh Kumar is a prominent academic associated with the Indian Institute of Technology, Kharagpur in India. He is known for his contributions to the fields of statistics and operations research. At IIT Kharagpur, Dr. Somesh Kumar serves as a faculty member in the Department of Mathematics, where he engages in both teaching and research activities. His work often focuses on areas such as statistical inference, decision theory, and Bayesian analysis. Over the years, he has published numerous research papers in reputable journals and has been actively involved in guiding PhD students. We are really lucky to have you, sir, Dr. Somesh Kumar, to chairing the session today. So with great joy and honor, I cordially invite you, sir, to chair the session. Over to you, sir.
Thank you. So I will firstly like to introduce Professor Hira Lal Kaul. Although I think many people in this community, they know him because he has been actively attending the sessions as well as the physical mode also he has come many times. Professor Hira Kaul is emeritus professor in the Michigan State University. He did his master's from Pune University in 1964 and his PhD from University of California, Berkeley in 1967. And from 1968 onwards, he has been a faculty member in 1968, firstly assistant professor and then associate professor. And from 1977 onwards, he has been a professor there. He's a fellow of American Statistical Association, Institute of Mathematical Statistics. He is an elected member of International Statistical Institute. He has been a president of International Indian Statistical Association as well as Indian Statistical Association. He has been co-editor-in-chief, associate editor, and editorial board member of large number of reputed journals. He has written 3 monographs and he has also edited some volumes. He has more than 150 research papers and he has produced more than 35 PhDs. in statistics. His main area of interest is inference on stochastic processes, non-parametric and semi-parametric inference, reliability theory, and survival analysis. For today's talk, he has chosen a topic on estimation in a randomly right-censored model. So I invite Professor Kaul to deliver his keynote lecture.
Thank you everybody, and hello to everybody there. And thank you to Professor Satish Kumar for keeping me in the loop. It's always a pleasure to talk in these meetings. So I'm going to now see if I can share this screen. Oh, wait a minute. Mm-hmm.
Yes, it is visible now.
It is fine, Professor.
No. But is this visible? Is this visible?
Yes.
Yeah. Now it is fine.
Okay,
Full screen. Yeah.
Full screen. I'm going to read this way.
Screen.
So today we'll talk about estimation of randomly right-censored errors in variables linear regression model. A model that regresses the response variable y on the predicting variable x is called an errors in variable model or regression model when x is not observable, but we observe something called z in an iterative manner. Z equals x plus u, where u is a measurement error. On the average, z estimates x, then the mean of u has to be 0. Now that's errors in variable. Then you have right-censored model, where we do not observe response y, but we observe something like minimum of c and y, and whether y is before c or not. So here c, the random variable, typically assume that is conditionally independent of y given x. And such models, randomly right-censored errors in variables regression models, are of significant practical importance in many sciences, including economics and health science. As evidenced in the monographs of Fuller, Carroll et al., and this 4 or 5 author book, it's about 900-page book, mostly to do survival analysis and health-related studies, whereas many models in these books have to do both economics, nutritional studies, and things like that. Yet, to date, inference in these models has lagged behind. In case of randomly right-censored linear regression model with no major error, then x is observable, several authors have proposed estimators of parameters. Back in 79 and 81, these also provide some estimators. And these two types of estimators coincide if you have one sample location model or two sample location model. Then later on, much later, these also provide much more a general class of estimators that include these estimators and develop a rigorous theory of proving the sort of normality of those estimators. And these authors studied further. This estimate is developed by these three authors, Cole, Sullivan, and Ryzen, using marginal techniques. So I'm going to focus on this KSV estimator. It turns out this is the least square estimator in a heterostochastic regression model. We'll discuss the bias character version of this sequence of estimators suitable in the presence of major matter in the covariates and proves consistency under some appropriate conditions. So our models, here's typical linear regression models, a simple linear regression model in the stock, but we don't observe X, we observe Z in the major matter in the iterative fashion. And basic assumption from identifiability point of view has to be that epsilon, X, and U are mutually independent, and mean of U is 0, and epsilon is mean 0. And variance is finite and non-negative for major matter, and positive for true covariate. And this is assumption one needs to develop estimators. But these three here, these assumptions are basically needed for identifiability. This one especially for identifiability purpose. Now we don't observe Y, but we observe minimum and delta. Let's have this notation. GXC is the probability conditional distribution X or C given X. And we assume this is less than 1 for all C in R. We denote absolute distribution of epsilon. Then conditional distribution function of Y given X is going to be this. Now here's a fundamental identity. It was first observed by Susada and Van Rijs in 1978 in the location model case. But then we extended that to regression case. So let's define this variable here. Y tilde delta divided by this entity here. And let's calculate its conditional expectation given X. So we said distribution of Y is conditionally independent of C given X. So therefore, conditionally X, Y and C are independent. So I integrate this way then. First integrate C, then integrate Y. So now you integrate C first, then what do you get here? You get C goes from Y to infinity, or so to say. So you have therefore this entry numerator, but we already have that in denominator. So that cancels due to this. Then by change of variable, you get this formula here. But we know mean of epsilon is 0, so therefore this is equal to that. That is fundamental identity. So if you know a conditional mean of a variable, given some other variable equals something like this, that means the regression of y, v on x is linear. So in other words, we have a new linear regression model, v equals this, but now we cannot quite say whether zeta is independent of x or not, but we know that conditional mean of zeta given x is 0 because of this relationship here. And now if I replace x by z plus z minus u, because z equals x plus u, then I get this model here. So here's another linear regression model where now this covariate z is observable, but error is here, but error is not independent of z, but it's uncorrelated with z. That's another way to look at it this way. All right, so then you may say you have a linear model, then why don't you just replace in the least square model estimate of beta alpha, replace x by z? What happens then? Okay, let's see. So this is a notation. These are S sub z diagram of the covariance sample covariance kind of things. So now we typically have data, and suppose for the time being gx is known. This family of distributions, conditional distribution function of c given x are known. So then v is completely observable. So then we can take v and apply classical idea of replacing xi by zi's and get the least square estimate of beta. Call it beta tilde. Now what is wrong with this? Well, it's not consistent with beta. Okay, now our assumptions imply that x independent of y and y being conditioned by x given c imply epsilon is independent of c. To see this, let's look at this. The conditional distribution function of epsilon joint distribution function of epsilon is c given x. Well, that's equal to replace what epsilon is. Epsilon is really y minus alpha plus minus x beta, or this event is equal to this event then, y less than equal to t plus alpha plus x beta. Now remember the assumption that conditionally given x, y and c are independent. So I can factor this out. But then that again, probably epsilon is less than equal to t. So therefore, this is that. And then, as for ABC, take this unconditional probability, takes expectation of this equals this, which is equal to probability 2 probability. So under given assumptions, epsilon is in T. Okay, now let's recall again, y is like this is a function of x and epsilon, and v is then function of y, x, epsilon, and c. So zeta is also a function of x, epsilon, c. But we know that there's independent x, epsilon, c being independent of u, therefore imply that v and zeta are independent of u. So therefore, we know this is the case. Expect conditional mean of zeta given x is 0 by the construction. Now here's expect xv is now. Therefore, from this fact, SUV, which is this, by law of large numbers, tends to 0 in probability. SU zeta tends to 0 in probability because there are sums of independent random variables with these mean properties. SUX will tend to 0 in probability, and this tends to sigma x squared, and this will tend to 0. So, therefore, and SXV, which is this, but remember, an expected XV is equal to this. So this product here tends to x x v. This will tend to x bar x bar and x bar v bar or v. So if you do algebra here, you get beta x squared, sigma x squared. So SXV tends to this. Now, why do you do all these calculations? To show you that beta tilde is inconsistent for beta. How? Okay, there's one more fact here. Because remember, z equals x plus u, x and u are independent. Therefore, the variance of z is sum of the variances, sum of the two variances. All right, so let's now look at beta tilde. Now, SZV, therefore, is this. Now, we just said SXV converts to 0. No, sorry, XXV converts to beta x squared. SUV, so SXV converts to beta sigma x squared. SUV tends to 0 in probability, so this will tend to beta x sigma x squared. Therefore, beta tilde, which is this estimator here, will tend to this plus this, divided by this thing. So therefore, this is not equal to beta. So therefore, beta tilde is not consistent for beta. Well, the standard term is x sigma u squared here. So take SDZ, subtract sigma u squared. In this case, the errors in variable or major error model to be identifiable. Besides those assumptions of independence, you have to have some characteristic knowledge of some characteristics of distribution of u. One of them is that sigma u squared is known, or some other characteristics maybe. Therefore, this beta hat now, because of similar calculations as before, will be constant beta. So this is called bias characteristic least square estimator. If these were originally x's, then this will be called bias characteristic least square estimator. No, sorry, v was y's, but these are now, I would call it bias characteristic estimator. Well, it's right now we don't know gx. All right, let's go further. I'm now going to discuss normality of beta hat first. So this, by algebra, this can be written like this. Now I'm going to analyze the numerator here first. So let's write SDV again like this. But once this adds to 0, there's no alpha then. This adds to 0, therefore there's no alpha. The first thing is this times this, so that's same as beta SXX. Second term is this times zeta I, that's SX zeta. Then third term is this times XI, that's SUX, there's beta there. And then there's SU zeta. Then there's SZZ here. So SZZ is equal to this. Now I'm going to multiply this by beta and subtract. So this term is the same as in the numerator here. And that, if you do the algebra here, you take this, see this beta SX, and you take it here, you get beta SX here, you get cancellation, that cancels out. So the first term gets SX zeta, then you have beta minus, then you have beta SUX, but you have then minus 2 beta SUX, 2 beta SUX, so you get minus 1 beta SUX, like that. So I gave this name Tn. So therefore, I know that this denominator converges to sigma x squared, by Slutsky, I can therefore say, but this entity here is approximately what is this here. You have a sigma x squared. So again, I'm writing the same expression here. Now let's look at the numerator Tn again. derive its limiting distribution. So first is root n times this term here. And now you see what is wrong. They are not quite sums of independence because there's the bars here, right? So you have to get rid of those bars. So if an adder subtract the mean of x is here and mean of zeta is here, so to say, and do some algebra, the rest of terms will be shown to tend to zero in probability. So you get essentially this thing here. You can see, first of all, this times zeta bar is zero. Sum of those is zero. So the first term is really this, but then you place of xi, mu x, or mean of x, is this one. Second term, you get this times beta ui, so you have this one. All right. So that's what this is now here, this sums of independence. Similarly, this term here, root n times that, is like approximately sums of independence like these. And third term, so therefore this root n Tn is approximated by some of these entities here. So to find these new random variables, call them Wi, which is this term plus this term ui, zi, minus there, right? Minus this term. Then root n Tn is approximately like sums of these independents, probability. But what is now W? It's a typical copy of that, and it's now you want to compute variance of W. So when you compute variance of W, you have to worry about what happens with cross product terms. It turns out mean of all cross product terms is zero. By the independence of u and zeta, and the fact that conditional mean of zeta given x is zero, almost surely, all the cross product terms, moments of summers in W are zero. Just to give an example, let's look at the first cross product term. This times this. I call it xc, center x, times this, times u zeta. So just multiply this. So xc zeta square u. That's this term here. Then you have beta xc u square zeta. Now condition this expectation by x, then x will stay here. And u is independent of x, so it doesn't matter. It just comes out as expected of u. So now we know the mean of u is zero. So that is zero because of that. And here, again, the same thing. But we know the mean of zeta u x is zero. So this is zero. Like that, mean of all cross product terms will be zero. Therefore, variance of W will be sum of these variances. Okay? And now we're assuming that variance is finite. Therefore, by sums of independence, by classical central theorem, therefore, this estimator, so to say, will converge in distribution normal random variable with mean zero and variance sigma W square sigma x4. So what are the conditions needed for finiteness of sigma W square? So I'd like to spend some time on that. So then I write sigma W square again here. Now you can see we have the assumption that fourth moment of x and fourth moment of u is finite. So therefore, these two terms are finite by that assumption, right? But we have the sigma zero square here and this entity here. We need to worry about what are the conditions needed for the finiteness of this term and this term. Oops. So let's define delta x to be this entity here, and then x is again. Now assume these four conditions. Remember, x is random, so expected value of this is x here, also there's delta x here. So these are the four integrals we need to have finite. Assume that. Then, under these four conditions, sigma W square is finite. Well, we know first these are finite already. I mean, under this condition and this condition here, so sigma x square is, the sigma W square is finite. So let me show you first sigma zeta square, what happens with that. So let's look at first mean of v square given x. Now remember what we did when we mean of v given x, where it was integration of c first. Then you get one of these terms here. It is typo, there should be sub x here. And therefore the extra factor here now. You get extra in the denominator here, extra 1 minus gx. And if then we change a variable again, we get this integral here. Now, you know this inequality generally, so Cauchy-Schwarz inequality, a plus b squared less than 2a squared plus 2b squared. Apply that to numerator here. Well, not yet. Okay. So now we go to tau x squared is conditional variance of zeta squared given x. And you replace that by here. Okay. So sigma zeta squared is an x plus tau x squared, which is this. This clearly, you can throw this term away, doesn't matter. But apply this inequality to this sound numerator here. This is 2s squared, the next pair of this entity here, plus 2 delta x squared. And there's I1 and there's I2. So since those are finite, therefore this is finite. So the first two integrals being finite in previous slide imply that sigma zero squared is finite. Now let's look at this other term. Oh. Okay. Sorry. Look at this term here. This xc squared. Tau x squared, we know what that was. There was this one. But again, this is finite. No need to worry about this. What about this term here? You look at it again, you apply, expand what this was here as before. And to this, then you apply the inequality, and you have 2 delta x squared as xc squared here. So you again, then there's I3 and I4. So those four conditions imply then these things are finite. Now let me give you a simpler condition in some special cases. Typically in practice, covariate is under your control, predicting variables under your control, and typically they can be assumed in a bounded range. If you do assume that, suppose gx doesn't depend on x, gx does not depend on x, so it's some distribution function g, and x is a bounded random variable. Then we know this is less than 2k, then delta x is less than some number d called, which is this here d, which is non-negative. And because g is monotonic, this is bigger than or equal to this, or therefore 1 over that is less than 1 over that. So then I1, this x, there's no more x here now. Therefore, it is just this entity here. I2 is this entity here. So you can see this same kind of thing appears either with 1 here or a square here. So if you assume just one, this integral with s square is finite, then that will imply this is finite. So in this special case, much simpler conditions implies finiteness of the sigma w square. It's supposed to have this kind of condition. Okay. So if you have fourth one x and it's okay. Now, here these ij's are finite if gc is minus or less than 1 for all c in R, and this happens. So summarize then, in the case of boundary design, and when g does not depend on x, and but g of c minus less than for all c in R, and this condition holds, and this condition holds, then that implies sigma of w square is finite. And we can this condition by verifying it only on 0 infinity is finite. So alpha less than 1. Then you can check this is finite. So there are many interesting examples where you can discuss estimate when G is or Gx is known. All right, now let's go further. So when there's no major matter, in the right sensor linear regression model, there's no major matter in the covariate. This also assumes C to be independent of Y. That means Gx is identical with G for some G. Then they use beta hat, which I call beta KSV. what is Kaplan estimator? What you do is take this y tilde, order them, and then let delta subbracket parents I denote corresponding delta i's. Then the Kaplan estimate G is this entity here. Okay. And now you define VI hats. Then the case estimator is classical linear regression estimator. Well, because remember we had this V as a linear regression model, so you do this. That's what we did in 1981. But then, well, now we have extra factor that X is not observable, and we then therefore make bias corrected version of this estimator. The bias corrected version in the current setup is then this entity here. Okay. So now question is this consistent? So what is the new technical challenge? Your V hats there. So nothing changed in the denominator. This will still converge to sigma x squared. But numerator, what happens to that? So let's look at the difference. Remember, beta tilde had SCV in numerator. So look at the difference. So only difference is that you have G hat in this case in denominator, well, you have this G in this case. So if I do some algebra, well, do simple algebra here. Then now you see, if I take this delta I, yi tilde times divided by this entity, that's my VI, right? So this times this divided by this is VI. So now we see, look, suppose these entities were not here. Just for a moment, pretend they are not there. Then what would this converge to? It will converge x plus z and v minus x plus z and x plus v. But x plus v, well, that converges then therefore to this. This numerator, this zi vi will converge to this x plus one. This thing we did that earlier. And therefore, you can say this is bounded in probability. So similarly applies d bar, then just apply second term, and therefore what I do is take absolute difference here. Before that, we recall a fact or a couple of facts. Although I say this follows from Zoe, but it really essentially follows from Gill's work in 1981. And these are two facts. Then we hit and multiply this root n, and I have this factor here in denominator. Then there's a random variable sequence random uniformly bounded in probability, uniform in I. And this ratio converges to 1 also uniformly in I. Remember, even if two randoms converge to each other, ratios need not, but there's some technical challenge in proving this, but this is the facts. And then under some additional conditions. Once you have that, then this absolute difference, take absolute value, I can pull out the maximum of these things, right? Is less than this. So, but I know this is of the order of 1 over root n. Remember, root n times that is bound in probability, therefore this will tend to 0 in probability. Whereas this is bound in probability, so this tends to 0. And we know denominator already tends to this, so therefore we right away have consistency of this bias corrected KSV estimator. Okay. And now I'm going to describe this extension, but now it's more challenging. And also to crystallize the conditions needed for this argument. He's a young, ambitious student who was willing to work at it. But anyway, so I'm going to describe now the extension of this to multivariate setting. Anybody has any question at this point? Okay. Now, so let's take P vector X, but we still have that P, all of them are not observable. So you have this matter model. Now you have this zero vector of means here. Again, same kind of assumptions. And now the difference only small sigma is replaced by capital sigma sub X. It is positive definite. Sigma u, which is this, is non-negative definite. In any theory you develop, you have to include the case of major matter. That means the sigma u could be zero matrix. Now we observe z y delta, this vector of z's, or zi yi tilde delta I from n observations. And now assume again C the independent of epsilon x and u, and independent of y. Then the bias, in this setting, the bias corrected estimator is this here. And the consistency follows straightforward in the same way. Under those conditions. Okay, these are references. There is this, 4-author book here. And this is about 900 pages book. Now I'll tell you a small story. This is for young people who may be procrastinating their research. In research, timing is everything. We submitted this paper in 79 November to the annals. In 79 December, this paper appeared. We are lucky that we did not know about this paper. Otherwise, we would have to justify why we're writing this book. Although the two estimates are totally different. And timing is everything. In research, hard work, but timing. If you have an idea, don't sit on it. Just get it out as soon as you can. Don't wait. Okay, now this problem of major error has been around just for a long time, at least for 120, 25 years. And there was a lull in that research. It kept going up and down in 30s and 1930s, 1940s. Neyman worked on this, Neyman Scott and other people. Then in 1984, there was a award lecture by T.W. Anderson, who wrote a 50-page review paper. That created more activity in the area, and then finally we got a book by Fuller, 87. And since then, what happened, Ray Carroll got involved in nutritional studies with NIH, and what he found that there's a lot of measurement error in the data. For example, somebody asked, what did you eat yesterday? How many calories did you eat? You have no way of keeping track of it, or how much fat you have taken over a lifetime. There's no way to get an idea of that, but you could keep a record for a few days and use that to predict how much you might have eaten. So he found in many nutritional studies there's a lot of measurement error. There's a first version of this book that came out in 1996. That time, this author was not there. Oh, I forgot the initials of this. But these three authors were there. Then they revised it in 2006. So there's a lot of activity in this, and even now, many estimators' procedures are not that, especially now if you're random censoring also, then life is much more challenging. And anyone who's interested in following the area, this paper must read this one. And so this one here. Journaling, and they've developed some good techniques for proving things. Then there's some other references, but that's in random censoring only. All right, thank you. I'm done.
Yeah, thank you, Professor Kaul, for a wonderful presentation of this estimation in the right-censored error in variables model. So you have nicely given this estimation part and also the corresponding theory. It also shows the probability distribution theory behind it, which allows you to prove the consistency and other things. So I think it is a good lesson for all the young researchers that actually everything is not just doing some simulation and other things. I mean, you really need to prove some theorems. That is there. I think it's a good presentation. I mean, good lesson also.
Thank you. Thank you.
So I invite now any of the participants to whether they have any questions. Mr. Vishwakarma, do you have any question?
Not so, sir.
Oh, okay.
Yeah, I have listened Professor Hiralal several times, and I was.
Yeah. Okay. I mean, if there is no other question, I would like to just ask. Maybe it may be a stupid question, but I just wanted to know.
No question is stupid question. No question is stupid.
So I just wanted to ask that because the first slide I could just not see all the steps there. So what about the distributional assumptions that you are having? I mean, is it for normal or the theory?
No.
Is more general theory.
Capital F, and the distribution epsilon is totally unknown.
Okay. Yeah, fine.
Okay. Only that some of those integrability conditions have to be satisfied. Those integrals I had. So there's some interplay between F, the error distribution or distribution Y given X, and the distribution sensing variable. Those integrals I had I's.
Yes, I have seen that part. Latter part I have seen. Yeah, that's correct. Yeah.
So let me go back to presentation more. I'll go to show you what I mean by that. See, if you look at these.
Yes.
So there's an interplay between F and sensing distribution.
Yeah.
So F is totally unknown. We had to assume Gx is known to just to motivate the estimator, because this has to be in denominator of V variable, right? So otherwise, later on, I see why also, if suppose this Gx depends on X, it's much harder to estimate the conditional distribution.
Yes.
So that's why then if you take eventual challenge maybe to do that, but initially you start with G not depend on X, and that's what we did. We estimated G then later, and so typically this condition again in this special case here, there's still interplay between F and G. So now I did say it's like see in like this condition here, but see in R, that assumes basically F is distribution on entire real line. But suppose that there's a support set of F which is not a real line, then this has to be true for C less than that support set of F.
Yeah, right.
So you have to make sure that this there may be some S where this is 0 and this is not 0, then you have trouble, right? So that way you have to balance these things out. That's what this condition here is in this special case, right? Here, if you don't have a less than 1, then you don't have this test, but it's not fine.
Okay, I have one related question. I mean, for small samples, any work is there?
No theoretical work. For small is impossible.
Yeah. Okay.
Because you have so many. First of all, you have infinite dimensional parameter unknown F.
Yes.
Right. Now somebody might have done assuming if it's normal, G is normal, then done something. I don't know anything available for that one.
Okay.
But now another point about this estimator is this KSV estimator. I mentioned this estimator by Buckley and James. That is an estimator which uses iteration to solve certain equations. They themselves reported that when they created this the solution, they found the solution oscillates between 2 values. And as a result, it's very difficult to implement that in practice. And higher if you have P more than 1, P more than 2 or more. No, alpha, beta, okay. P more, 2 or more actually. That is much worse. So the Buckley estimator is efficient at Gaussian error distribution. But then in the one sample location model, the two estimates coincide, ours and theirs coincide. I mean, actually ours. KSV estimate and Buckley James estimate, they coincide.
Okay. Okay, thank you. Yeah. So are there any other questions? If there is no other question, then we conclude this session. And once again, thank Professor Kaul for such a wonderful presentation and an exciting talk, basically. So let's thank him.
Thank you.
And with this, we come to a close of this lecture.
I just want to say one more time, thank you to organizers for including me, and it's always a pleasure to be in the meeting here, and always nice to listen to other people also. Thank you all. And good to see you, at least virtually, see you, some of you.
Yeah. Over to Professor Satish Kumar.
Yeah.
Thank you, Professor Hira, for your wonderful talk. We are very much grateful to you, Professor. In fact, it is very informative and useful to the researchers, especially those who are interested in working on that area. And also for beginners also, there's several things are there they can go and find. Great, Professor. Great. In fact, we are very much thankful to you, Professor. Also, we wish to extend our gratitude to Professor Somesh Kumar for chairing the session and making the session a very vibrant through your deliberations in that respect. And in fact, I have placed some more time after this talk because someone will interact more. That's why what I expect. So
hello, Sudesh.
Yeah.
Sudesh, you are there? Sudesh?
Yes. Sudesh is also there in the group. Yeah.
I just seen it.
He's muted.
Mute your.
Yeah.
Yes, sir.
Visible.
Okay, you have a challenge.
Yeah.
Okay,
Actually, I just reached Chennai from ISA Kolkata. So, but I didn't miss you. Fortunately, I came at 6 o'clock itself. So.
Okay, all right.
Yeah.
Now you know what you have to do, right?
Yeah.
Dig back the old version and throw the other estimate out. Work on this one.
Yeah.
Okay. I have not written this up yet, but I was going to write and send it to you later.
I informed
Good to
Professor
see you.
Bala also and join, but he has also some other commitments.
I see.
Professor Balakrishna from Kusai. No, he's in Tirupati. No, Kusai. Also.
Okay, then I take your leave. I have to attend one meeting actually.
Great, it's very great to see you.
Okay, Professor. Okay, Professor.
Yeah.
Many of you.
So bye to all of you.
Yeah, bye, Professor. Bye. I hope we can wait for some more time for the another session.
What time is next talk?
Yeah, Professor. Yeah.
What time is the next talk?
Next talk, Professor Vikas Tinka. Vikas.
What time?
Now 14 minutes. 10 more minutes.
Okay. I'll be back. I'll just take a
yeah,
break.
by 10 minutes. Yeah. So let us get a relaxed 10 minutes. Yeah, Professor Vikas.
नमस्कार
Hi.
कैसा है भाई साहब सब ठीक है तो
Namaste.
एवरीथिंग ओके नमस्ते गजेंद्र या
Nice to see you, sir.
थैंक यू सेम विथ मी
So you are in India, sir, or abroad?
आई एम इन द यूएसए नाउ
Okay, sir. So when you are coming, sir?
कमिंग
Is there
एंड
any
ऑफ द
plan
ईयर
for New
मोस्ट
Year?
प्रोबब्ली
New academic
most
year?
probably end of the year
Okay.
most probably end of the year yeah
December.
Yeah, it will be end of November or early December, right?
Okay.
দিলীপ কেমন আছো ভাই?
ঠিক আছে দাদা, প্রণাম জানাচ্ছি।
আচ্ছা, ঠিক আছে।
He's also there in US now.
Yes. Yeah. Oh, is that so? Okay. Visiting his daughter or?
Yes.
কোথায় আছো এখন?
শিকাগোতে।
শিকাগো, আচ্ছা, আমি তো শিকাগো দুলালের কাছে গেছিলাম।
কবে এসেছিলেন?
মাসখানেক হলো আর কি।
হ্যাঁ, আমার কিছুদিন আগে দুলালতে কথা হয়েছে আমার।
আচ্ছা, ওই দুলালের ছেলের বিয়ে হলো, সেই সময় গেছিলাম।
আচ্ছা আচ্ছা, শেষ।
Okay, so Satish Kumar, I'm here.
Yeah.
Okay, no
Yeah, Professor.
problem.
Okay, Professor. Let us wait some more time because some people also planning to join by that time. That's why.
Professor Satish Kumar,
Yes, Professor.
can you send me schedule to for today's day 2, please? Oh, that's over now anyway.
Today
And day 3 and tomorrow's schedule also.
Yeah, Professor. Again.
Program. I don't have that.
Okay. So I shall send you. And in fact, there is a program chat we have already sent, in which everything is there, Professor.
So, Satish, please make sure there is somebody to operate on the screen sharing.
How are things in Kolkata?
Kolkata is hot and humid. But yeah, I was there till the end of April. Then I came over to Dallas, Fort Worth area.
Oh, you're here. All right.
Yeah, I'm here. Yeah.
Hmm.
In the same time zone as Chicago.
Right. Hmm. Did you go to Pune meeting in May?
No.
Hello, David.
Hi, Hira. How are you?
All right. Good to see you.
Thanks.
Hi, Satish.
Yeah, it was right. Okay, Naina, just let us start the session. Naina, please introduce the chair and
Okay, sir.
chair to run the session. Yeah, please.
She has to unmute.
Naina, please. Oh, yeah.
Hello everyone. We are moving on to the technical session 13 of WSTA 2024, which is a keynote address that shall be chaired by M. Kumaran. Kumaran sir is currently working at Kannur University. We are really lucky to have you, sir, for chairing the session today. So with great joy and honor, I cordially invite you, sir, to chair the session. Over to you, sir.
Kumaran sir. Please unmute your mic, sir. Hello, Kumaran sir. Kumaran was?
Kumaran sir, your mic is muted. Kumaran Mash, your mic is muted.
So whether he joined or not, because I'm unable to see in the list.
Yeah, he is in the list. There's a Kumaran M. Like this is here in the group. I shall contact him via.
Yes, he is here.
Mr. Riyad, call him over phone.
Yeah. I'm calling.
Yes, sir, okay.
By the time we can share the screen and he will join immediately. Hope so. He has some network issues. That may be the reason.
Okay, sir. Okay, sir.
Should I go ahead? Hello.
Just a minute, Professor. Okay. Just a minute. He is calling. He informed that he is there in the group, but his voice is, there is some audio problem, so he couldn't voice is not audible. That is what he is trying to say something. Once again, let me to contact him whether it is clear, or otherwise we can move to this talk.
But we are audible. We can listen. We can hear.
Yeah, Professor. Whether his sound is audible to you?
It is. Yes, I can hear it.
Not his.
Not me.
Yeah, I cannot hear either. So, but anyway, because he is well known, so we can listen to his talk.
I cannot hear.
Professor Satish Kumar?
Hello, yes, Professor.
Because he is well known, so he needs no introduction.
You can introduce to this mobile if you want. If the other way is not audible, please introduce through this mobile so that we can. Hello.
Okay. Good evening to all.
Sir, we can hear you.
Okay. Okay. Now, let me introduce our eminent speaker of the session, Professor Vikas Kumar Sinha. Sinha was a faculty of ISI, Kolkata for a long period, for 32 years. He retired in the year 2011. He took his PhD from Calcutta University in 1972 and started a career in the same department. In 1975, Professor Sinha's illustrious career started in the form of teaching, training, research, consultancy all over the world. His quality of teaching and collaboration research earned him international recognition. What awarded the P.C. Mahalanobis Gold Medal in the year 1980. He became an elected member of International Statistical Institute in 1985. He was appointed in as expert on mission for the UN Statistics Training Program on Survey Methodology in the year 1991. In 1993, he was appointed as a consultant for the U.S. Environmental Protection Agency. In 2006, he was nominated to serve as a member of the National Statistical Commission, Government of India, the highest policy-making body for Indian statistical system. He served as a visiting faculty research collaborator in several universities in the US and Canada. During each of the 8 consecutive summers, 2011 to 2018, he was invited by the US Census Bureau for research collaborations. After retirement, Professor Sinha traveled all over India with the aim of population statistics among students and faculties. Professor Sinha has collaborated with more than 110 research collaborators worldwide, and he still continues to mentor academics at different universities, institutes on various research collaborations. A very eminent statistician, Professor Sinha, used to deliver a talk on linear and quadratic regression in the light of de la Garza phenomenon. Now, I invite Professor Sinha sir to make his presentation. Thank you.
Thank you, Mr. Chairman.
Professor Kumaran, yeah.
We are delayed little bit, but it's okay.
Yeah.
We are all going together. Okay. So I'm referring to, sorry, you want to say something?
No, Professor, you please continue you please begin your talk, Professor.
I'm referring to...
40 minutes you can take, Professor, for your talk.
Okay. Yeah, I'm referring to a name here, as you can see, De La Garza. De La Garza, this gentleman wrote a paper 70 years back in 1954 that came out in Annals of Mathematical Statistics. That was the name earlier to this Annals of Statistics, Annals of Probability, etc. So why am I referring to that? Because I want to make sure that the students and the young budding research scholars, they get the spirit of the work that was done so many years back and that still has relevance in future research. So I'm talking about linear and quadratic regression. Next. Abstract we can skip. Next. These are the different sections that I'm going to take up. Next. Yeah. There is a nomenclature. My idea is to show this thing, not to scare you, but to tell you that there is a long-term thing going on in this area of de la Garza phenomenon. So what is this phenomenon and why is it that important? I'm going to touch upon this thing. So the first one is a monograph. Second one is a book well-known book by Puckelsheim. Next two are papers, and everywhere this phenomenon has been discussed in a serious manner. Next. These are the books. The Optimal Design of Experiments, that's the book by Puckelsheim. Then our monograph, then a paper in statistical science. The last one is a paper in Annals of Statistics in 2009-10. So these are all relevant references that I'm showing and using. Next. Let us start with a motivating example. In a very first course in linear regression, we teach our students y equal to x plus y equal to alpha plus beta x plus error. And then after 1 or 2 lectures, we give them data set and analyze the data. So data always looks like this: x and y. Fit a linear regression equation of y on x under the usual model assumptions. This is the mean model alpha plus beta x, and we assume homoscedastic errors. We know the computations center around the 5 summary statistics, and thereby we can estimate alpha, beta. We also have an estimate of the error variance sigma square. So everything comes in order, and we teach our students about the basic inference problems, testing of alpha and beta, and talking about estimation and other parameters. So everything is very routine, straightforward, no problem. Next. A smart student in the class asks a thought-provoking question. So I have kept this student by the name Rakesh. The motivating question is, if we believe in the linear regression model, y equal to alpha plus beta x plus error, and if under homoscedastic variance and all that, what good are so many x values? I think I started with 7 x values. Why can't we work with exactly 2 distinct values? So that is the question posed by a student in the class. So while all of them are doing the computation, this boy, he has something in mind. He wants to know, why can't we work with exactly 2 distinct values? Because there are only 2 parameters, alpha and beta. But the collective wisdom of the students in the rest of the students in the class, they point out immediately, well, you watch out the error degree of freedom, that is 5 in this example, so we can compute sigma square hat. Now what happens if we have just 2 observations? Then there is no degree of freedom for error, so there is no estimability for sigma square. So what are we talking about? Next, so this is the immediate reaction of the group of students, rest of the students in the class. What he is saying possibly does not make sense. Next. Clarification given by I did not quite mean that. I meant, for example, you take 2 distinct x values. For example, you take minus 0.7 and 3.5, for example, and load them with the frequencies 4 and 3. So minus 0.7 x value, you take 4 observations there, and 3.5 x value, you take 3 observations there. So altogether, you will be getting 7 observations. That is what you are doing. But I tell that you take this minus 0.7 with a repeat and 3.5 with a repeat. Then 4 IID observations at x equal to minus 7, that will provide 4 minus 1, that means 3 degree of freedom for the error variance. Likewise, 3 IID observations at x equal to 3.5, that will provide 3 minus 1 or 2 degrees of freedom for error variance. Therefore, I can always think of the additive property of chi-square, and I can combine these two together to get 5 degrees of freedom for the error variance. That's all you have been doing anyway. So this is what I wanted to say. So that is the immediate reaction of Rakesh. He says, this is what I have in mind. Next. So this prompted a question, given 7 distinct x values, these are the 7 values listed there, how can we get hold of a value like minus 0.7 with a repeat number 4 and another value 3.5 with repeat number 3, or some such 2-point solution with adequate frequencies? The 2 points could be different from what he suggested. He's just trying to give the illustration and the concept. And then he's saying that it could be the frequencies could be 4, 3 or something adding up to 7. So what do we intend to accomplish by carrying out this exercise? Then the teacher takes up. I know a whole lot of theory. I can explain what is going on. I will take up from here. I thank Rakesh for this kind of mature thinking in the very first course in linear regression. Next. So digression for a moment. This is the linear regression model. Usual conditions apply to the errors. Don't bother about complicated scenarios. After all, this is the simple-minded, stat-loving teachers and learners. Matrix notation, go slow. Y equal to x theta plus e. Theta is the vector alpha beta. And x is the design, called design matrix. The first one is all ones corresponding to alpha. And the next one is all the xi's corresponding to beta. So this is my simple, we all know all these things. Next. And then as advanced learners, we start with Gauss-Markov model, y, x, theta, sigma square I. We know the descriptions of all these things going on. I theta is the Fisher information matrix, x transpose x. I theta is a squared symmetric matrix. In this case, it is of order 2 and it is of rank 2 whenever xi's are not all equal. We know how the positive definiteness comes. Next. Fisher information matrix, that is capital I. We can for the moment, we can take away sigma square. So this x transpose x, that is this 2 by 2 matrix. Small n is the number of observations. T1 is summation xi, T2 is summation xi square. And if we think of averaged information matrix per observation, we divide by n, and the moment it becomes a moment matrix. 1, mu transpose 1, which is the first moment, and mu transpose 2, which is the second moment. So all these things are well known. Next. Rakesh possibly claims something like this. Given 7 distinct x values, such as x1, x2, x7, there exist 2 values x star, x double star, and condition 1 says that x star and x double star, they are captured within the data range x1 and x7. They are captured in this range, and then there are corresponding frequencies f star, f double star. Both of them are positive integers, so that summation xi, the first moment referring to summation xi, that is equal to x star f star plus x double star f double star, and summation xi square is equal to this thing what he wrote, sum of squared observations x stars with corresponding frequency. So that would mean that the information matrix based on the original 7 observations IX will be identically equal to information matrix based on X star. X star is composed of, capital X star is composed of X star, F star, X star, F star, and X double star, F double star. So this is the value in the X space. These are the values in the X space, and these are the frequencies, suitably chosen frequencies adding up to little n. That would mean that there is information equivalence going on in this case if instead of 7 distinct values, we make use of 2 values only with suitable frequencies. The question is it always possible to find out X star given X? Now, the choice of this X star is dictated by, given X, naturally, by the number of observations and the X values themselves. And X star, of course, it amounts to, as I said, X star, X double star with corresponding frequencies. So given capital X in the form of n and xi's, when is it possible to come up with X star, X double star, F star, F double star, to make it information equivalent to attain Ix equal to Ix star? Next. So this is the question that is bothering Rakesh, and he possibly has this thing in mind. And even in a most general form, under linear regression, given small n greater than equal to 2, such that x equal to x1, x2, xn, not all xi's being necessarily distinct, there exists this pair such that this is the first condition. The second condition refers to f and f star f double star adding up to n. Third condition refers to summation, and fourth condition refers to the sum of squares. That would mean that two are equal. Is it always possible to find out x star given x? That is the question coming up. Next. And in that context of relevance is the work done by De La Garza, as I said 70 years back. There are research papers in Annals of Statistics, the Springer monograph I showed, Wiley book, Optimal Design I showed, continuous flow of papers involving linear and non-linear models, both qualitative and quantitative responses, enormous impact of De La Garza phenomenon in optimality studies. Next. So De La Garza's paper deals with what is called continuous design theory. So we can think of the context, same context, linear regression model, the capital X, as I showed, that's known as regressor. The space of the regressor we are taking to be a closed finite interval, AB, and there are k at greater than equal to 1 because we are under linear regression. So k greater than equal to 1 distinct x values in this space of chi, and they have got positive, all these k values, x1, x2, xk, they have got positive OH or mass, W1, W2, Wk adding up to 1, and continuous version of IBR will be, I will be replacing by mu prime 1, which is the first moment, mu prime 2, which is the second moment. So it talks about a space of regressors, distinct x values on the space, and then having positive OHs. Rather than having frequencies, we are talking about positive OHs adding up to 1. Then the continuous version of the information matrix, that would be in terms of mu prime 1 and mu prime 2. This is known as the information matrix arising out of a continuous design in terms of, this is how we describe a continuous design, xi, wi. Wi's are the mass distribution of the x values. Next. De La Garza phenomenon in the context of continuous design theory. Linear regression model with homoscedastic errors. Claim, given any continuous linear regression design, what is the meaning? D is the design, K is the number of distinct x values, and these are the x values sitting here, and W is the corresponding weight functions W1, W2, up to Wk. So, given any continuous linear regression design with k distinct support points in this space, in this interval, xi is all distinct with positive weights, etc., such that they equal to 1. Whenever this k number of data points, whenever this k is more than 2 in the framework of linear regression, we can always find exactly 2 points, x star, x double star, with suitable weights, p star, p double star, such that x star and x double star are covered inside the data range, x1 to xk, and then p star and p double star, those are the weight functions adding up to 1. And on the top of that, the information matrix based on x star, that means x star, p star, x double star, p double star, is identical to the information matrix based on the design that we start with, d of kxw. So De La Garza phenomenon, it refers to continuous design theory, it refers to information equivalence, study of information equivalence. I just wrote the simplest thing, namely linear regression model. That's why I'm talking about k equal to 2, k more than 2, and then getting two values, x star, x double star, etc. Everything is related to linear regression. Later, I will talk about the quadratic regression, but it will be only up to that. But the theory is profound, and it talks about any polynomial. In fact, de Lagarde's paper itself is a very thought-provoking paper. Talks about a lot of things. Anyway, so this is the claim made according to de Lagarde. Yeah, you can always find, you give me kxw, I give you x star, x double star, p double star, so that the information matrix becomes identical for both original D as well as the built-in D star. D star is based on two values and corresponding probabilities. This is the expression for D star, and this is the D original. Whenever k is greater than 2, you can come up with exactly 2 points. Next. Proof of this claim, I think I will skip the proof. It's not at all difficult, but anyway, a good lesson for the beginners. Anyway, I will skip it. Next. Yeah, proof continued, etc., etc. Next. Yeah. So if we apply this phenomenon, we can try to understand what is happening here. So what are A and B in this data range? These indicate the range of values of X. As I said, this is the closed interval. In our example, if we go back to the data, you can see right here, this is the original set of data, minus 3.2 up to 8.2. See, in our example, A is minus 3.2 and B is 8.2. There is a unified approach. We can always change from X to U, and this is the form of U, 2 times X minus A over B minus A, whole thing minus 1. That makes U between minus 1 to 1. And this leads to capital X as a function of capital U, a linear function. And therefore, this you can see what U values are. U values are minus 1, 2, plus 1, and assuming values like etc., etc. These are the intermediate 5 observations transformed into U. If we talk in terms of U, that simplifies our thought process. Whatever X be, we always define like this, and we come to minus 1 to 1. And then we can see what is the first moment, which is the second moment. All these things we can compute. Next. So to understand de Lagarde, there is a condition given that P star, one of the P values, will lie in between this and this. So you work out the numerical values of mu1, mu2 prime, and you get left hand side, right hand side. We need a choice of P star between this and this. Now, after making a choice of P star, we know P star will be some frequency divided by 7, because after all, there are 7 observations here. So we have to make sure that my choice of P star is such that 7 times P star is an integer. And this is the unique choice 4 over 7, which is 0.57. So that suggests F star to be 4, F double star to be 3, and the values of U star, U double star in the according to the proof. So this is U star, and this is U double star, and they can be converted into U, converted into X, lower and upper. So I get X star minus 2.05, X double star 6.67. So what is the bottom line? Given 7 distinct X values, as we saw, we can always come up with exactly 2 distinct values, X star and X double star, with the corresponding frequencies 4 and 3, which implies information equivalence. So that is the spirit of de Lagarde. Next. So this is the final result. Under linear regression with homoscedastic errors, X, the data set, is equivalent to X star. You see the repeat of minus 2.05 and also the repeat of 6.67 in the sense of information equivalence. Now the basic question is, what is the guarantee that n times P star will necessarily be an integer given any discrete design with a total of n observations. What would have happened in case we are in the framework of quadratic or polynomial regression? So, but before that, we can take up some interesting results in the context of linear regression itself with small samples. Next. These are the things, when you work on it, you really feel what is going on, and then you feel motivated and you try to come up with examples, all kinds of examples here and there. What does it say? It says, so I'm giving a 3-point design. I give you a 3-point design. You are saying that you can apply de Lagrange and you can claim that you can get 2-point design. So give me a 2-point design so that the two will be information equivalent. So the first one says, I give you -1, 0, 1, each with frequency 1, single count. The total is 3. It is impossible to replace it by a 2-point design for information equivalence. On the other hand, if I have -1, 0, 1 with frequency 2 each, then I'm getting 6 observations. Now it is possible to replace this by a 2-point design. You can see not possible, possible, all kinds of things are going on. Next. De Lagrange exact design theory. This aspect somehow has been bypassed in the literature. Difficult to provide a general theory as to the exact sample size for information equivalence to work. In order that the information equivalence works for discrete designs with frequency counts, etc., then we need to have a general theory. So that general theory, it was not considered seriously. So in a paper, we took up this study, and this is what we did. We said, okay, let us talk about -1, 0, 1, and let us talk about W-1, W0, W1, +1, attached mass so that they add up to 1. Then we can always find a 2-point design, say A, P, B, Q. A and B are the data points in the interval -1 to 1, and P and Q, of course, they add up to 1. We can always find a 2-point design. That is what de Lagrange is saying, such that, next, such that A and B are between -1 to 1, and P and Q, they add up to 1, and there is information equivalence between the two designs. What if we are in an exact design scenario with a given total number of observations n, and its decomposition into n minus, n and n plus, being assigned to -1, 0, 1. So if you go back, please go back 1. Yeah. So here I'm talking about the exact design theory in the context of de Lagrange phenomenon. So whenever I write W-1, W0, W plus, adding up to 1, there is no difficulty in applying de Lagrange result and getting the weights W-1, 0, 1. Straightforward. Also to find A and B, P, Q, everything is there. But the moment you replace them by the exact design theory, that means talk about the sample size, then it becomes a problem. Next. So I'm referring to this. I give you a total of small n. I give you a total of n minus, n0, n plus, attached at -1, 0, and 1. Now you tell me, how can we find the solution A, NA, B, NB? These are the 2 data points out of 3 and satisfying. Next. So A and B are between -1 and 1. NA plus NB is n, both being integers, and there is information equivalence. Do we need a condition on n at all? Sample size. Crucial observation is not all values of small n are amenable to establishing the equivalence theorem of the information matrices in the exact sense. Needed a minimum sample size. Only then it works in the exact sense. So there is a big difference between the approximate or continuous design theory and the exact design theory dealing with frequency counts. There we need a condition on small n. Next. A general theory for 3 points with point symmetry. Consider a general allocation design -1, 0, 1. Okay, my purpose in showing these things is not to say that it is trivial, but to point out that these are interesting phenomena going on here. And if someone wants to dig into this and then do further research, there's plenty of opportunity to work. So let us consider a general allocation design -1, 0, 1 with frequency counts n minus, n0, n plus, etc. They add up to small n. We want to replace the above 3-point point symmetric design. It is a point symmetric design because I have got -1, 0, 1. These are the 3 points that I have chosen. So it is a point symmetric design. So I want to replace this by a 2-point design of the form A, N, A, B, N, B, so that Na plus Nb equal to N, and moreover, information equivalence holds. What does it suggest? Next. Now, so then if I look at the information matrix, then A, Na plus B, Nb, that is the summation xi, and on this side it is -1, 0, 1. Therefore, the sum total is n plus minus n minus. And then when I take the sum of squares, it becomes a square n plus this equal to now -1, 1. They both give +1. So I hope this is clear. Now I am doing the simplification, all kinds of algebra coming up, because my purpose is to come up with A and B and Na and Nb. Given this, that's the whole idea. This total is n minus n0. Anyway, so this is what is known. From this, there are 2 equations. My unknowns are, there are 4 unknowns, but there is another condition, n plus plus n minus plus n0 equal to n. So we have got n0 is there. Even though n0 does not show up here, it shows up in the expression for n. Okay, so you said something and then go on simplifying and go on getting expressions for a, b, n plus, n minus. Next, I'll skip the algebra, etc. Next. Next. Yes, let us look at this. Finally, it comes to this. There is a quantity called capital L, and capital L is equal to, it refers to the inequality, but basically there are 2 quantities, capital L and capital U. It starts with capital L and it ends with capital U, lower and upper. So there is a quantity called capital L, which is computed based on these p-values. P-values are nothing but the relative frequencies, n plus divided by n, that is p plus, n minus divided by n, that is p minus, and n0 divided by n, that is p0. So you compute a lower quantity, lower value, and an upper value. And one can show that this and those 2 are captured in between, and in between those 2, I have captured a quantity called capital A in terms of capital A over little n. So I can rewrite it as NLANU, and this A has to be an integer. So I have to make a choice of capital N in a way that this interval captures an integer, capital A. Next. Choice of small n must be such that the interval NLNU includes at least 1 integer which can serve as the value of capital A. A sufficient condition for this to happen is, of course, that the length of the interval n times U minus L, that the length of the interval is greater than equal to 1. So if there is an interval which has length more than greater than equal to 1, then I can always find an integer in between NL and NU. That's the whole idea. Even otherwise, a choice of A could be assured, but that we have not been able to focus. We are able to find out a value of small n so that this thing is greater than equal to 1, and that serves our purpose of identifying the quantities in the equivalence theorem. Next. So here I give all kinds of examples. Okay, please let us go one by one. Yeah. So here I take up point and mass symmetric distribution. And what do I get against that? That is the what we invest. And what is the return? Return we are looking for small n equal to 3. It cannot be replaced by a 2-point design. For small n equal to 3, you cannot get a 2-point design. For small n equal to 6, yeah, you compute NL and NU and you find that there is an integer, and therefore you can find a solution, and that always been mentioned in the chart. Next. Okay, let us skip these things one by one. Okay, yeah, goes, yeah. So for n equal to 9 again, you get some, there are 2 integers, therefore 2 values. This solution is, the starting point is P0, P plus, P minus. You can see that it is point symmetric, but not mass symmetric, because P plus and P minus, they are different. It is point symmetric, but mass asymmetric. Here again, you can work out and you can see what can be achieved and what cannot be achieved. Everything in terms of the existence of this small n, and then finding out a solution to capital A. Next. Next. Let me tell something about the quadratic. Next. Yeah, next. Yeah. Next. Next. Hopefully quadratic is coming now. Yeah. Quadratic regression information equivalence. Context. Quadratic regression model with homoscedastic errors. Plain. Given any continuous regression design. D stands for the design. K is the number of distinct data points. X is the specification of those data points. And W is the corresponding mass distribution, W1, W2, Wk. So given any continuous regression design, D, K, X, W, with K support points in this range, etc., Xi is all distinct, and with positive weights Wi's, whenever K is greater than 3, up to K equal to 3, I have no problem, because there are 3 parameters anyway. But whenever K, number of data points, is more than 3, we can find exactly 3 points. So these are the 3 points that I have mentioned with suitable weights, P star, P double star, P triple star. That is what I have given the notation. Notations are horrendous, but contextually these are clear, such that the entire X values are in the data range and their total is 1. And then the information matrix for the original KXW 3x3 information matrix and the one based on X star, P star, X double star, P double star, and X triple star, P triple star is identical to the information matrix obtained from application of DKXW. So this is the theorem going on here. And de la Garza has proved this theorem not just for quadratic regression, but for a general polynomial regression. That paper is rich in contents in terms of matrix theory. Lot of matrix results are involved over there in order to prove these things. So he has done a thorough job of proving the existence of, even in the context of a polynomial regression design. Next. Quadratic regression, exact design equivalent, information equivalence. So this is what we have in mind. Given K distinct values, such as X1, etc., corresponding frequencies of K, it could be right over here, there could be repeated data in general formulation. Subject to their sum equal to small n, the summation Fi equal to small n, that's the number of observations. There exist these things such that they are in the data range, their frequency counts, they are up to small n, and then the sum total is this, and sum of squares is this. So the question is, for discrete design like small n and F1, F2, Fk, this is the discrete nature of the design. Continuous nature of the design would have been P1, P2, or W1, W2, Wk, as I said earlier. But now we are talking about a discrete design in F1, F2, Fk. Can we get all these F star, F zero? This is what we are looking for, the values and the corresponding frequency counts, such that this thing happens. Is it possible to get it all the time? Next, quadratic regression, that would mean this, etc. So the question is it possible, always possible to find out X star given X? Choice of X star is dictated by X, namely in terms of N, K, F frequency counts and X size. And X star amounts to these things subject to the conditions that have been listed there. So this is the main problem coming up here in terms of exact design. Next. So there are some kinds of results here. Go slow, start with basic results. For example, problem number 1, it says I have a point symmetric design -1 + 1 -a + a, and also I have a mask symmetric design if each data point has only one observation. So there are 4 observations. How can I reduce it to a 3-point design with information equivalence? That's what I'm saying. Can we find X, Y, Z, and then corresponding frequencies like without any loss, the total frequency is 4, so I have to have 2, 1, 1. It is impossible. Then I'm saying under D of 6 means there are 6 observations like this. If I have the problem number 2 given that this, then we can find this X and F, everything can be found. There is a unique solution. So like that it is going. Next, I think I will go slow. More on quadratic regression next. I stop. Okay, let's see the next one. Yeah, here I stop. Okay. So there is this reference paper. This paper written in 2013. It was conceptualized. This idea was conceptualized in a casual conversation with my long-term collaborator Nipesh Mondal, and then we also got Professor Monisha Pal. They are both in Calcutta University Department of Statistics, and that is where we sat, and then we could find out finer aspects of the de la Garza phenomenon in the exact data analysis, in small samples. De la Garza thing refers to large sample because they are referring to the continuous design, but we refer to the finite sample size design. How can we get this information equivalence? So the statistics and applications, that are Delhi-based journal, ISRI, over there, and then so that was published in 2013. But the spirit of that problem still continues, still haunts me, and once in a while I try to go back and see how much is the progress. I will stop now. I thank Satish Kumar for the opportunity given to me. I hope the students and the research scholars will benefit from this very basic idea, but there are problems.
Thank you, Professor. Thank you so much. Thank you so much. And the chair also informed me to carry over the remaining part. So if there is any questions, one question can be, I hope, otherwise it will, yeah. Yeah, please.
Hello, may I ask a question? Or
yeah,
that was a lovely talk. I had not heard of the de la Garza phenomenon before, but it's a fascinating thing. Let me inquire, if you're doing polynomial regression with degree greater than 2, do similar results obtain?
Yes. As I said, de la Garza took up the continuous design in terms of W, and then his result covers up to any degree polynomial. So if it is a kth degree polynomial, y as a function of x, kth degree polynomial means number of parameters including alpha. It will be alpha, beta 1, beta 2, beta k.
Right.
So altogether k plus 1 parameters. So you have to have k plus 1 data points. So de la Garza says that if it is more than k plus 1 data points, we can bring it down to k plus 1, exactly k plus 1, with the revised weights to get information equivalence. And then there is a concept of information dominance. Dominance occurs when the 2 points are at the extremes. This very famous result by Puckelsheim. So one says equivalence, other says dominance. Information dominance will be there if the number of support points is exactly equal to number of data points.
Thank you.
And
I
that
think Srivastava had raised his hand as well.
Sorry, say it again.
Yeah, thank you, Professor. Professor Rakesh Srivastava has raised a hand.
Okay.
Whether you want to say anything, Professor?
Do we have time just for 1 minute?
Yeah,
Am I audible?
Please, one, yeah.
Yeah, you are audible. Tell me.
Okay. Good evening, Professor Sinha. This is Rakesh from Baroda. Sir, I was just wondering that we are talking about in simple regression analysis. Is it possible to have some extension to multiple regression analysis also? And the second quick question would be that how will you go for the interpretation of the regression coefficients?
Good question. Now talking about multiple regression, yes, it is there in the book by Puckelsheim. He talks about multiple linear regression. Multiple regression means X1 different in a number of component covariates. He talks about that. But as you know, response surface exactly does that. Quadratic response surface, it takes up Y as a function of X, a multiple number of covariates, and there it goes up to the quadratic form. So there are studies in this area. So yeah, as I said, the regression designs, particularly the y equal to alpha plus summation beta I xi plus summation ci xi square plus double summation dij xi xj, all kinds of things are there in the design books. So we talk about the regression designs and polynomial regression designs. Yeah, it is there.
Okay. Thank you, sir.
Thank you, Professor Bikas, for your excellent talk. And we are very much grateful to you, Professor. And in fact, we extend our gratitude to the Professor Kumaran, sir, also for chairing the session in a very nice way. I hope everyone is now ready to move to the Professor David Banks' talk.
Okay. Very good.
Yeah, Professor. So I'm sure there are several questions maybe there from the audience. Those you can interact through other media, email or in future. Okay. Sorry for the time because we have 1 or 2 minutes it will left.
Okay.
And Swapna, please.
Yes, sir.
Please introduce the chair. In fact, Professor Arivarignan sir is here in the group. Yeah, okay. If he is not, he has informed that some urgency, so that Kalyanaraman sir will chair this session. To Professor, please just give a brief introduction to the chair and support the chair.
Hello everyone. We are moving on to the 14th technical session of WSTA 2024 that shall be chaired by Dr. Arivarignan. Now, Professor Arivarignan head to the Department of Applied Mathematics and Statistics at Madurai Kamaraj University, Madurai. He has published more than 9. Sorry, sir.
So now, Professor Arivarignan sir is not here in the group. He has some urgent matters. So, Kalyanaraman sir will chair this session. Okay.
Oh, okay, sir.
So please just introduce Kalyanaraman sir Kalyanaraman sir. Professor Kalyanaraman is a faculty professor of our department, University of Kerala. He is always with us as a lighting force, and I invite Professor Kalyanaraman sir to chair this session, please.
So, good evening to you all, and I welcome Dr. David Banks David Banks obtained a PhD in statistics in 1984. He won an NSF postdoctoral research fellowship in the mathematical sciences, which he took at Berkeley, working with David Blackwell. In 1986, he was visiting assistant lecturer in the University of Cambridge and then joined the Department of Statistics, Carnegie Mellon, 1987. In 1997, he went to the National Institute of Standards and Technology, then served Chief Statistician of the United States Department of Transportation, and finally joined the U.S. Food and Drug Administration 2002 as the lead statistician for counter bioterrorism in 2003. He returned to academics at Duke University. He was the coordinating editor of the Journal of the American Statistical Association. He co-founded the Journal of Statistics and Public Policy and served as the editor. He co-founded the American Statistical Association section on national defense and homeland security, and has chaired that section, as well as the sections on risk analysis, the statistics learning, and data mining. David Banks is past president of the Classification Society of the International Society for Business and Industrial Statistics. He has twice served on the board of directors of American Statistical Association. He is a fellow of the American Statistical Association, of the Institute of Mathematical Statistics, and of the American Association for the Advancement of Science. He won the American Statistical Association Founders Award, the D. Root Award, and gave the William Seelig Gossett Lecture and the Deming Lecture from January 2018 to September 2021. The director of COMSI. His research areas include models for computational advertising, dynamic test networks, adversarial risk analysis, and Bayesian behavioral game theory. Human rights statistics, again, agent-based models, forensics, and others. So I now invite Dr. David Banks to the table.
Hello, everybody. I apologize for the long introduction. If I do this again, I will shorten it so we don't use so much time. Are you able to see my slides? Satish, Professor Kumar, are you able to see my slides?
Yeah, Professor.
You can. Excellent. And
I am not able to see them. How do I see them?
Advance the slides?
No.
No? How about this?
I don't see them.
You do not see the slides. Oh, okay.
No. Slides not at person.
Do you see the slides now?
No.
No, person. No.
Okay, now yes.
Yeah.
Now you do. Okay, great.
Now yes. Now it's fine, person.
Yes.
Okay, excellent. Thank you so much. Good evening, everybody. Thank you for taking time to be here today. I'm not quite sure how to advance the slides, but I'm interested in a problem in sequential decision theory that I can represent as a Bayesian graph traversal when there is an opponent. Okay, let me see. How do I advance this now? Did the slides advance? Good, thank you. All right. Classical game theory has focused upon adversarial situations in which the outcomes are generally known, and when uncertainty addressed, it makes very unrealistic assumptions that both of the parties have common distributions over the actions of the other. And it also turns out that game theory makes very unreasonable assumptions about human behavior. Behavioral economists such as Kammerer and lots of others have made it very clear that human beings do not reason as a game theorist says that they should. In contrast with game theory, we have statistical risk analysis. And classical statistical risk analysis has focused upon situations in which the opponent is non-strategic. So you're trying to do a risk analysis for the damage that a hurricane causes, or the risk analysis of what a flood will do. And a hurricane and a flood are not intentional. A flood doesn't decide to move in one direction as opposed to the other, neither does a hurricane. So in contrast to those two situations, I would like to propose something called adversarial risk analysis. And that's a decision theoretic alternative to game theory, and it's based on Bayesian statistics. And the idea is, the idea in adversarial risk analysis is you build a model for the decision-making of your opponent, and then you make the choices that maximize your expected utility against that model. And because you're a Bayesian, you place a subjective distribution over all the things that you don't know about your opponent. And this is incredibly controversial. Roger Myerson has a Nobel Prize in economics, and he hates this. He says that a fundamental difficulty may make the decision analytic approach impossible to implement. And the reason is because in order to analyze the optimal strategy, a player would have to determine what all the other players would think would be his optimal strategies. And that, according to Roger Myerson, means that you would force the player to abandon the decision analytic approach and instead undertake a game theoretic approach. And I think that is throwing the baby out with the bathwater. It's much too premature to revert to game theory, especially given the fact that we have tons of empirical evidence that human beings don't reason as game theorists say they should. So in adversarial risk analysis, you build a model for the decision-making of your opponent, and you use that to develop a subjective distribution on their actions. And I will pause for a moment to note that that is the way we all operate all the time. Suppose you're asking your boss for a raise. You have a mental model for what that boss values. You've known the boss for a long time. You're a Bayesian. You have ideas about what the boss thinks is important. You may think that the boss values good paperwork, punctuality. You think that the boss values that you show up every day and work for 8 hours. And if you have that correct model of your boss, if that's correct, then you have a good chance of getting your raise. But if you've misread the boss, and what the boss really values is how many clients you have, how much money you bring into the firm, then your chance of getting a raise is probably pretty small. So this is how we operate all the time. We have models, we project what we think other people in our lives are, how they're going to react, and then we sculpt our own actions in order to maximize the response that we want. So with that context, I will note that adversarial risk analysis conveniently partitions the uncertainty in a problem into three components, each of which can be addressed separately. There's aleatory uncertainty, which is the uncertainty in the outcome conditional on the choices of the opponents. So if I make one choice and somebody else makes another choice, and then we see what's going to happen, it could still be random. For example, Coke and Pepsi can be regarded as two opponents, and Coke could decide to try and open up a new product line in potato chips, and Pepsi could decide to open up a new market in China, and then the net profit for those companies is still a random variable conditional on the choices that they have made. And that type of uncertainty can be handled by regular old school statistical risk analysis. That doesn't mean that risk analysis is easy, but we know how to do it. Epistemic uncertainty arises because we do not know what the utilities of our opponent are. We don't know what the capabilities of our opponent are. We don't know what the opponent values. And so as a Bayesian, we can put distributions, subjective distributions, over all of those unknown quantities. One of the important ones is the probabilities. Is our opponent an optimist or a pessimist? So I can place a subjective distribution over that, and then I will choose the action. I'll have these subjective distributions, and I will devise those by using Bayesian self-elicitation. So that's the way you handle epistemic uncertainty. The more novel and interesting situation is concept uncertainty. And in concept uncertainty, I'm saying I do not know how my opponent is trying to frame the problem. Does my opponent want to find a game theoretic solution? Does my opponent want to act in a non-strategic way? Is my opponent using level 1 or level 2 thinking? We'll talk about level 1 and level 2 thinking later on in the talk. But there are a number of different strategies that an opponent could use, and I don't know which one they're trying to include. Greg Parnell and Jason Merrick compared probabilistic risk analysis with various intelligent adversary methods, and they preferred adversarial risk analysis largely because we were able to partition the total uncertainty into 3 components that could be handled separately. And they found that enabled more transparent modeling and more intuitive results. So one example of Bayesian graph navigation with an opponent concerns convoy navigation with improvised explosive devices. So we're going to support the defender, who's the convoy planner. And this defender has beliefs about where improvised explosive devices might be put. And the attacker, an insurgent, has probabilistic knowledge about the route choice that the convoy planner will use, the value of the convoy. The payoffs for the attacker and the defender are going to have additive structure, such that if you have a convoy that is hit by 2 improvised explosive devices, then the damage from those 2 is cumulative. So that's the idea of having additive structure. Somebody's got an open mic. If they could turn their mic off or mute it, that would be great. Thank you so much. So in this context, Y is the defender, the convoy planner's known loss matrix. And that says how much the defender values losing a truck, having a soldier die, that kind of thing. X tilde is a random matrix, which the defender uses to model the attacker's gain matrix. And that random matrix is going to have a distribution F. So the defender does not know how much utility the attacker gets from a successful attack on the convoy. But the defender has a subjective distribution over that gain matrix, and that's going to have this distribution X tilde. Y tilde is what the defender thinks the attacker believes is the defender's loss matrix, and that's going to have a distribution G. The attacker does not know the true Y, but the attacker presumably has some beliefs about how valuable that convoy is to the convoy planner. And the defender does not know what those beliefs are, but as a subjective Bayesian, the defender can put a prior distribution over those, and that matrix is going to have the distribution Y tilde. A tilde is the random vector that the defender uses to model the attacker's decision. It's going to have distribution F, and that's going to determine where improvised explosive devices are put. R tilde is the random variable the defender uses to describe the attacker's belief about the defender's choice about the route that the convoy is going to take as the convoy navigates this road network with IEDs. So in this context, the adversarial risk analysis algorithm is going to take X tilde with distribution F, Y tilde with distribution G, and A and R are going to be in the support set of where the attacker can place the IEDs, that's A, and where the defender can choose the route, that's R in D. And so you start off with some initial pair of probability distributions, P naught and Q naught. And P naught is going to be a distribution for A tilde, Q naught is going to be a distribution for R tilde. And then you update that such that you find A star equals the argmax of script A in set A of A transpose times X tilde times the expected value under Q sub K of the route choice. And then you plug that in and you find and you're going to wind up getting the argmax down here. And then you're going to do the same thing in the reverse direction to find R. So you're going to find R according to the argmin of the expected value of A tilde transpose times Y tilde times R, and that's going to have distribution Q K plus 1. So we've updated P K to P K plus 1 and Q K to Q K plus 1. And you keep doing that loop until the P sub Ks and the Q sub Ks don't change very much. And at that point, you terminate the search, and now you use your true loss matrix, Y, not Y tilde, in order to make the choice R star, the route choice, that's going to maximize your expected utility for your true loss matrix Y. And there are a couple of theorems that come out of this. One is that a mirroring fixed point solution for the system of equations exists. So, and actually that's not an easy thing. In classical game theory, being able to prove that there is a solution is not necessarily trivial. And secondly, if there's a total ordering on A and a total ordering on D, such that AX tilde R and AY tilde R have increasing difference and decreasing difference respectively, then the adversarial risk algorithm is going to converge to the mirroring fixed point. So this algorithm will converge. And it turns out that that second theorem is going to be true. It is always true if a loss for the attacker is a gain for the defender, a loss for the defender is a gain for the attacker. So if you have anything, well, that's stronger than a zero-sum game. But certainly it's true for zero-sum games. It's true whenever the signs of the payoff matrices are opposite. And it's even true when many, but not all, of the signs in the payoff matrix are opposite. So that's a pretty powerful result. I now want to broaden out to a different class of problems. This has to do with network navigation, where we have a traveler who knows the adjacency matrix of a graph, and she knows the vertex at which she is located. And each time an edge is traversed, there is an unknown cost. The first time a node is reached, there is an unknown reward. And the traveler has prior beliefs about the distributions of the costs and the rewards. And if the traveler backtracks over an edge, the previous cost is assessed. And the traveler's goal is to stop when the expected future revenue is negative. And this class of problems is quite general, and it captures many situations in sequential decision-making. One application is portfolio analysis. You are a money manager. You can invest in a series of stocks. When you decide to sell a stock and buy a new stock, there's a transaction fee, and you would like to try and trade stocks until you don't think you can make a favorable trade going forward. Another example is when you are an undergraduate student and you're picking the courses in your college career. And when you decide to enroll in calculus, you don't know how much it's going to cost, and you don't know how much benefit it's going to give you. Certainly calculus is going to be a hard course. It's going to take time. So there is that cost. On the other hand, if you do well in calculus, that will open the door for other courses that will benefit you later on. Similarly, if you are looking at your career, you'll have a choice of jobs that you can take. And based on the first job that you take, you may have opportunities to take a second job later on. And you don't know what the long-term payoff of this sequence of choices is going to be. But all of those situations can be represented as a network navigation problem. Now, ideally, the traveler would consider all possible paths that start at her current position, and then she's going to calculate the expected net value of each path, navigate to the neighboring node on the path with the largest expected revenue, update her beliefs, and then reevaluate the situation. So that would be how a Bayesian would approach this. But one problem is that this is going to be impractical for anything other than a very small graph. That's because this type of infinite horizon calculation is going to be NP hard. However, we have good approximations based on Markov decision processes and partially observed Markov decision processes that allow us to do good approximations for the dynamic programming that's going to be the optimal solution. And now I am very grateful that all of you are listening to this, because I want to make an assumption. I'm going to assume that the traveler has a normal inverse Wishart prior over the joint costs and payoffs of the edge traversals and the node benefits. And certainly that's a very flexible family, because it allows her to express her uncertainty about both the mean and the covariance. And here's what I want to ask the audience about. It seems pretty obvious that the normal inverse Wishart family is closed under conditioning. If I have a p-variate normal inverse Wishart family and I observe the first component, then the conditional distribution of the remaining p-1 components will also have an inverse Wishart family distribution. And I have looked all through the literature to try and find that result. And I'm sure it's out there. I mean, it's not hard, but it's not in Press, it's not in Berger, it's not in Morrison, it's not in Hong, it's not in any of the standard places that I would have gone to look. I even found obscure PhD dissertations from South Africa that were all about the inverse Wishart family, but didn't address this. So just for showing it, if you have a p-variate normal inverse Wishart distribution, then we can write the density as the product of the normal density and the inverse Wishart density. I'm going to imagine that I observe the first k components of this, and I want to find the conditional density of the remaining k+1 to p components. I partition the mean and the variance in the sort of obvious ways. The conditional distribution of the xk+1 to p, given the first k, well, that comes from normal theory. It's going to have this mean, and it's going to have this covariance matrix. Using the Schur complement, I get sigma sub 2 conditional on 1. So given the first part, I get the covariance matrix for the unseen variables. And it turns out that I can write that out as an inverse Wishart. And I wind up getting the final k+1, given the first as being another normal inverse Wishart with this mean, this covariance matrix, and this precision. So that structure allows us to use dynamic programming with a finite horizon, and the length of the horizon depends upon the computational resource that we have available. And in practice, that determines on how correlated you think the neighboring nodes and neighboring edges are going to be. If they're tightly correlated, then you don't need to have a long horizon. If they're weakly correlated, then a longer horizon is going to be more important. So that is where we are trying to go with this. And now I'm going to imagine we've got a batch of little propositions. This is a work in progress, so it's not a final story yet. But one thing we did was to imagine that the traveler is clairvoyant. So there's no uncertainty in this at all. She has perfect knowledge of the net gain associated with every possible path, but still it's an NP hard problem. So a circuit is a sequence of edges such that the first and last node are identical. So the traveler makes a loop, and one can show that a clairvoyant's optimal path therefore repeats a circuit. You can also show that if there exist two circuits with the same endpoints, then at most one circuit is present in the clairvoyant's path. A cycle basis is a graph thing. It's the cycle basis for an undirected graph, which this is the minimum set of cycles that allows every even degree subgraph to be written as a symmetric difference of two of the cycles. An edge that is not present in a cycle in the cycle basis is traversed at most twice by the clairvoyant's optimal path. If the graph is acyclic, then the number of times a clairvoyant visits a node on this optimal path, her optimal path, is bounded above by twice the node's degree. And in practice, it's going to be less than that. Also, the length of the clairvoyant's optimal path does not exceed twice the number of edges. For very large graphs, especially if they have strong clique structure, one can use a clique graph for approximation. And the clique graph bundles sets of densely connected nodes into supernodes. And so you sparsify the graph by treating cliques of nodes as a single node. And for an adversarial risk analysis, we're going to assume now that the traveler has an opponent who can reduce the node reward or increase the edge costs. And one can model the opponent's interventions using the mirroring argument described previously, or we can use something called level 1 or level 2 thinking. And I will note that in general, the opponent is going to be better off increasing edge costs than reducing node rewards. And that's because with high probability, the traveler is going to traverse the same edge more than once. And that means that they're going to be paying the penalty more often. In level K thinking, that's due to Stahl and Wilson, they say that if the opponent is a level 0, then your opponent is choosing to change edges or node rewards non-strategically. So maybe they're reducing the largest payoff, maybe they're increasing the least expensive edge traversal. If your opponent is a level 1 thinker, then he believes that the traveler is a level 0 thinker. So he believes that the traveler is acting greedily, taking the traversal to a node which has the largest expected utility in that traveler's model. And in that case, the level 1 thinker, the opponent, is going to increase the cost of the edge traversal for the node that he thinks the traveler is most likely to use. And if the opponent is a level 2 thinker, then he believes that the traveler is a level 1 thinker who believes that the opponent is a level 0 thinker. And so she's going to take the second best path. And so the level 2 thinker is going to penalize the second best path instead of the first best path. And of course, in all of this, the opponent doesn't really know what the traveler's subjective beliefs are, but the traveler can have a subjective opinion about those beliefs. And since we're supporting the traveler, we're going to allow the traveler to have a belief about the beliefs of her opponent. And this all sounds complicated. For those of you who are fans of the movie The Princess Bride, we have this I think that you think that I think type reasoning going on. And that's like Vizzini's analysis of the iocane powder episode in that movie. And although this sounds intricate to talk about, in fact, it is simply a recursion. So it's actually very easy to program all of this. And I think that is a real advantage. Stahl and Wilson found that except in certain highly structured games, such as chess, people rarely go beyond level 2 thinking. If you're playing chess, you're going to look for many more moves than 2. But for regular human interactions, level 1 and level 2 are almost always what's done. And that was verified by a set of games that they did in a study of undergraduates at the university at Clemson University. So let me move on to some conclusions. The mirroring argument provides an explicit mechanism for modeling the reasoning of one's opponents. Unlike the common knowledge assumption in classical game theory, we instead allow you to say, I think that my opponent has this belief, and I think that my opponent believes this about me. And so I'm not having to assume that we have common knowledge, that the opponent and I both have a common distribution. I'm simply creating a model for what I believe about my opponent and what I think my opponent believes about me. So no telepathy is required. Previously, decision theoretic Bayesians who did game theory simply declared a distribution over the actions of their opponents, but this construction allows us to use either mirroring or level 1, level 2 thinking to actually derive a distribution over the actions of the opponent. Graph navigation is a toy problem, but it's actually very general. As I mentioned, it applies to things like portfolio management. It applies to things like picking your career. And finally, the full solution is going to be NP hard, but there are smart approximations which will produce good results in many sensible applications. So I am working to try and sort of finalize a paper, actually 2 papers on this topic, but I think this is a very natural way for people to think about a large class of sequential decision theory problems. So that's my last slide. I would be delighted to take questions. Oops. Yes, okay.
Thank you very much, Professor David Banks, for keeping time to the schedule. Now, the problem is before the audience. So you can ask some few questions because five minutes more are there. So people can ask any question if they are interested in.
In fact, let me ask a question. I would like to know if anybody can send me a reference on the normal inverse Wishart family being closed under conditioning. It must be out there.
Nobody is asking any questions. Sir, I may ask one thing, sir. I just want to know one term. Elicitation, what do you mean by that?
Oh, elicitation. Yes, thank you so much for asking that. Self-elicitation is a Bayesian procedure for developing your personal belief about something. So if I want to decide what is my prior on the stock market going up on Monday, I would ask myself a whole series of questions and use a sequence of wagers that would lead to me determining what my prior belief is. This really goes back to Di Finetti, who invented the idea of trying to conduct an infinite sequence of hypothetical wagers with yourself in order to determine what your subjective belief is. It's been developed by a number of other people. There is a long book by Tony O'Hagan and like 15 co-authors that lays out a whole batch of different approaches to eliciting self-elicitation of prior beliefs. It's a standard tool in Bayesian statistics. Jay Cadane, Laura Wolfson, a whole batch of people have worked on this. It's not easy. I'm not saying that elicitation is a straightforward thing, but it's something that Bayesians have been doing for, more than 70 years.
Yes. Any further questions? If no further, I thank Professor Banks for providing a wonderful lecture on navigation, and I hope that will be very useful for researchers in future. So, on behalf of the organizers, I thank you, sir, for taking all efforts to come and present a good paper. Thank you.
My pleasure.
So
Thank you.
over to Dr. Satish Kumar.
Thank you, Professor David. Thanks for your wonderful talk. In fact, we have time to discuss more, but even then, I think the next talk will be Professor Michael Evans is here in the group, but we have time. We plan to start it then 2050. Yeah. So just let us. We would like to extend our thanks to the chair, Kalyanaraman sir, also for sir. Thank you, sir. Thank you for chairing the session, and I hope just we can wait 5 more minutes because there is we have placed the time. Okay.
Hi, I'll just try my sound. Satish, can you hear me?
Yeah, Professor, yeah, we can hear you. We can hear you. Yeah.
Sometimes, I don't know, it's funny, some things, sometimes it works, sometimes it doesn't. Sometimes I have to use a headphone and microphone, but it seems to be okay this morning. Great.
Yeah. How is matters with Toronto, Professor?
Well, it's actually a little bit warm the past few days, right? Usually, I guess Toronto was thought of as being cold, but it's been quite hot here the past little while. But I suspect it's a lot hotter in Kerala. What would your temperature be there right now?
Yeah, in Kerala also different temperature as usual, but usually we have a not much extreme climate, but this time we have a too much hot.
Too hot, eh? Yeah. What would the temperature be there now in centigrade? Celsius?
Sure.
I just wondered what the temperature was there right now.
Oh,
during the day?
Around 30, 28. Now it's 28.
That's similar to what Toronto has been the past little while as well.
I was talking to a friend at the Chennai Mathematics Institute who says that they have been having temperatures over 50 degrees for like a solid month. It just seems unendurable.
That's brutal.
That's very, yeah.
So what is going on with climate change in India now?
Here in India, some places extreme climates, too hot and too minimum, cold also. But in Kerala, usually there's a medium temperature, not much usually. But this year, it is different. It was different. 2-3 weeks before, it was very hot, and it comes up to 40. Around 40, yeah. And thereafter, now the heavy rains comes, and now it is okay. It is little bit medium level.
Well, I'm glad to hear that the temperatures have come down with the rain.
Yeah.
What about North Carolina, David? Is it hot there?
Well, actually, I'm not in North Carolina right now. I'm in Brooklyn. Both of my kids, my granddaughter, all live in Brooklyn, and so we've got an apartment here, and that's where I spend summers and winter break. But yes, we have had a heat wave. The entire East Coast has had a heat wave. Temperatures got up to probably around 42, something like that.
That's hot.
It was hot, but compared to Chennai, I cannot complain.
Well, I often spend time in Singapore, and there it gets pretty hot and humid, but it never seems to get up into the 40s. They're near the equator, and I guess there's a ring of clouds around the equator that keep it reasonably cool. If you go north of Singapore, it gets hotter. I've noticed that.
In North Carolina, it's humid, and so if the temperature gets too high, it often triggers a thunderstorm, which will cool things down.
Yeah, that's like Singapore. It rains almost every day there.
That sounds like the same mechanism, yes.
Yeah.
How long a break do we have? When do you begin speaking, Mike?
4 minutes, I think. 11:15.
11:15. Okay, great. I should have looked at the schedule more carefully.
Yeah, I'm afraid I didn't too. I just got the tail end of your talk. I would have come earlier.
Oh.
Well, I like your mention of elicitation, because a lot of Bayesians don't really talk about elicitation, but it's a key part of the story, right?
If you're a subjective Bayesian, yes. If you're an objective Bayesian, then it's a different conversation.
Whatever that is.
Yes, I have trouble with that, but people I respect put a lot of store in objective Bayes.
Yes. There's a new book, right? I just got it.
So what's going on with your faculty, Mike?
Growing.
Good for you. We are not.
Well, it's probably going to taper off now, but the past few years, the department has just mushroomed in size. There must be almost 50 faculty members now.
Wow. We have lost 3 people who are all really, really good. And I totally understand and respect their decisions, but still, I wish they would have stayed. Satish, I think I saw Barry Arnold on the program, but has he spoken yet?
No.
No, he's not? Oh.
Well, yeah, let us start, Professor. No. What? Anything, Professor?
I thought I'd seen Barry Arnold on the program for this meeting. Is he going to be speaking?
Professor Barry's here, I think. Barry is not scheduled on the second morning. Tomorrow and day after tomorrow in India time.
Okay.
I shall send the details in the meantime. In the morning first talk, and the after tomorrow. And,
Thank you.
yeah. I think now let us start because we have 8:45, 8:44 now, Indian time, AST. I hope. Bhagya?
Yes, sir.
Yeah, now you can introduce the chair and do the needful for the session.
Sure, sir. Hello, everyone. We are moving on to the 15th technical session of WSTA 2024, which is a plenary session that shall be chaired by Professor Sangeeta Arora. Now, Professor Sangeeta Arora is a professor to the Department of Statistics, Punjab University, Chandigarh. Her areas of interest include statistical quality control, environmental statistics, and applied statistics. She is the recipient of the 8th Venus International Women Awards for Lifetime Achievements in Statistics in the year 2023. Also, she is a life member of Indian Society for Probability and Statistics and Indian Society for Medical Statistics. She has got a lot of publications and has been organizer for several national conferences and workshops. An excellent academician with about 4 decades of experience in teaching and research. We are indeed fortunate to have you, ma'am, sharing the session today. On behalf of the organizing committee, I extend a warm welcome to you and kindly request you to take over the session. Over to you, ma'am.
Good evening to everyone. So this is, I think, the last session of day 2. So this is a plenary session and we have eminent statistician, Professor Michael Evans for this. So I will just read out a brief out for the Professor Michael. Professor Michael is a professor of statistics at the University of Toronto. He received his PhD from the University of Toronto in 1977 and has been employed there ever since, with leaves spent at Stanford University and Carnegie Mellon University. He is a fellow of American Statistical Association. He served as chair of the Department of Statistics from 92 to 97, interim chair from 22 to 23, and as president of the Statistical Society of Canada from 2013 to 2014. He has also served as a member of editorial capacities as associate editor of JASA Theory and Methods from 91 to 2005, associate editor of Canadian Journal of Statistics from 99 to 2006 and 2017 till present date, and associate editor of the Journal of the Bayesian Analysis 2005 to 2015, and as editor also from 2015 to 2021. The subject matter editor for the online journal Facets Current and associate editor of the New England Journal of Statistics in Data Science currently. Michael Evans' research has been concerned with multivariate statistical methodology, computational statistics, and the foundation of statistics. A current focus of research is the development of a theory of inference based on an explicit definition of how to measure statistical evidence and the development of tools to deal with criticism of statistical methodology associated with this inherent subjectivity. He has also authored or co-authored numerous research papers as well as the books. So some books are Approximately Integral via Monte Carlo and Deterministic Methods with T. Swartz, published by Oxford in 2000. Probability and Statistics, The Science of Uncertainty with J. Rosenthal, published by W.H. Freeman in 2004, and Measuring Statistical Evidence Using Relative Brief, published by CRC Press, Chapman and Paul in 2015. So today he will be talking on the concept of statistical evidence, historical roots, and the current developments. So let us all welcome Professor Michael. So Professor Michael, over to you.
Thank you. Now I've got to figure out how to get my screen. Oh.
There's an upward arrow. There's an upward arrow.
There's in the bottom. There's an upward arrow.
Yeah.
Click on that, so that you can select the entire screen, and click in that small box, so that the share button will be active.
Okay. I hope this works. Can you see my slides?
Not yet.
Not yet. Yeah, there's some issue here. Sorry. Click the tab to share, which I'm doing, but it doesn't seem to do anything. Okay, maybe this does it.
You have to click on the share, only then it will be shared.
Share. Yeah, it just, maybe this will do it. Well, my apologies, but it's giving me, oh, here we go. Well,
Now it is okay.
Yeah, now it is fine, Professor.
Yeah. Okay, so I guess I want the full screen. Sorry about this. It's the first time I've used this.
Yeah,
Okay,
it is fine. It's excellent. Yeah.
Okay, great. Okay, well, thank you very much for the opportunity to talk. And my title of my talk is The Concept of Statistical Evidence, Historical Roots and Current Developments. This is more or less a review paper, and it's on a topic that was mentioned in my introduction that's dear to my heart, the notion of statistical evidence, because I think that's the core concept in statistics. But it's not really carefully treated. Okay, so just to point out that it's common to refer to statistical evidence as part of a statistical analysis. Here, everyone's familiar with phrases, the evidence and the data suggests, based on the evidence we conclude, or there is evidence against, etc. Many uses of this terminology, the phrase statistical evidence. But what is it? Suppose we had to provide an explicit definition, what would you say? I think currently the concept is vague, at least in many aspects of many fields of subfields of statistics, if you like. Whoops, I've seen. Well, do we need a precise definition? Maybe we can continue on without defining statistical evidence very exactly. Well, I'm going to argue no. In a scientific context, there's an object of interest, so I'll denote it by big psi. For example, I like physics examples. Maybe big psi is the half-life of a neutron, the mass of a neutrino, etc. And the scientist has collected data, which I'll denote by little x, and I'm going to always assume that this has been properly collected, believed to contain evidence concerning the answers to these questions they have. Now, what's the evidential approach to statistical theory? Well, there are two aspects, two questions really. The estimation question, we're asked to provide an estimate of the value of psi, so I'll denote that by little psi of x, with an assessment of the accuracy. And then there's the hypothesis assessment. There's a theory that suggests a value for psi naught. And what we want to know, is there evidence in favor of that being the true value or evidence against it being the true value? And we want to know how strong, we want to measure also a measure of how strong that evidence is. So the question is, if we get a definition of, another aspect of the question is, we have a definition of statistical evidence, how are we to reason from the data to answer these questions E and H? And for me, that is always based upon this definition of statistical evidence. Now we can contrast the evidential approach to what I'll call the decision theoretic approach. So I've drawn two boxes here. In the evidential approach, there's three subcategories: frequentist, likelihood, and by likelihood here I mean pure likelihood, which I'll explain what I mean by that a little bit later, and the Bayesian approach. Or there's the decision theory approach, which more or less subdivides into frequentism and Bayesianism, if you like. So my talk is basically concerned with the evidential approach, but I'll make some comments about decision theory as well. So what are the ingredients? If we could just reason from data, that would be great, but we need to add some things. And these are choices made by a statistician. So like it or not, we have to acknowledge that these are subjective. For example, there's the sampling model, which is a collection of conditional probability distributions for X, and X supposedly was generated from one of these distributions, which I'll denote by theta sub true. And of course, that means we can calculate the value of psi, this quantity that we're interested in. Tell me what theta is, I can calculate big psi of theta, and that gives me little psi. And so I'm interested in the value of big psi at the true value, the true distribution. And I'll just split here between evidential inference, which for frequentist and likelihood methods, what I call the inference space is basically just the sampling model and the data. Whereas in the Bayesian context, we add something to the inference space. The inference space, because that's what we base our inferences on. We add the prior. It's a prior probability distribution, a proper prior distribution in this case, on the parameter space. Now, in decision theory, whether Bayesian or frequentist, we add another ingredient, namely the loss function, which I'm going to call loss. And it's a map such that from the cross product of the parameter space and the set of values for the quantity of interest into the non-negative reals, such that it's zero if and only if psi, little psi, is the correct value when theta is true. Why evidential inference as opposed to decision theory? Well, there's two reasons really. First reason is, and this is not unique to me, but people feel that, well, losses in utilities are not really relevant in scientific applications. Really, we want what's the evidence in the data? When we add a loss function, there's some kind of, well, it's a choice, it's subjective. And another aspect of that, the subjectivity, is that whereas the model, we can check it against the data. It's subjective, it's a choice, but we can check it against the data, which if it's collected properly, we accept as being objective. Also, the prior we can check through checking for prior data conflict. But in general, how do you check a loss function? For example, y means y squared error, which is a very common loss function that is used in applications, right? So it's not clear in general how to check a loss function, although I will mention something at the end where the loss function can be checked against the data. And I'm going to carry along the following simple example, namely just a location normal, very simple example, but it's rich enough to show virtually everything that I want to say. So it's just a collection of normal densities with an unknown mean and known variance. And I'm going to make inference either about the mean or about the absolute value of the mean. And the reason I want to talk about the absolute value of the mean is because it's a many-to-one function here. And this introduces the problem of nuisance parameters, which is a plague for certain approaches to statistics. So the first thing I want to talk about, and just, like I said, this is a review paper. I want to go over the various attempts to talk about evidence within statistics and say what I think, and what others too, it's not unique to me, is wrong with those approaches. And the first approach is probably the most commonly used in statistics. That's the p-value. So what's a p-value? It's actually kind of hard to define, but I'll give my best crack at it if you like. So we have a statistic. I want to test the hypothesis that the true value of this quantity of interest, cap psi, is equal to psi naught. So I have a statistic, which I'll denote by t sub psi naught, the function of the data. And we look at its distributions under the null hypothesis, and we ask the question, is the observed value t sub psi 0 at x is something we would expect to see if psi naught is the true value? So we have to measure that somehow. And typically the way that's done is we say, well, large values are in the tail of the distributions. That's usually how the statistic is chosen. And we want to compute the p-value as follows, namely, how far out in the tails is it? That's what this probability here is doing. And I'm going to take the supremum of that probability over all the possible distributions that lead to making that null hypothesis true. And if that's small, I'm going to say I've got evidence against H naught. That's a typical use of p-value. And of course, a standard example, one of the first ones we teach in elementary statistics is the Z-test, and that's just what I have here for testing whether or not the mean of a location normal is equal to theta naught, right? So everyone is presumably familiar with that. Now, there are concerns with p-values, and as I said, it's not unique to me, and one of the places I like to read about that is Royale's book on statistical evidence in 1997. That's about the best discussion of the defects of p-values that I've ever seen or ever read, anyway. Now, the question is, when do we have evidence against H naught? It's not clear from the value of the p-value. We think, well, when it's small, that's evidence against, but how small does it have to be? So generally, we have to choose an alpha. And when the p-value is less than or equal to alpha, then we say we have evidence against H naught has been attained. And this, of course, is similar to the decision theory idea of accepting and rejecting a null hypothesis. Reject a null hypothesis when basically the p-value is less than alpha, and accept it otherwise. So there's a bit of confounding here between the evidential approach and decision theory, but we'll focus on the evidential approach. Now, what value of alpha? Well, in many fields, it's perhaps due to Fisher. I think he might have been the person who recommended it. Alpha has been taken to be 0.05. A couple of years ago, there was a recommendation from a group of statisticians to make it 0.005. And recently, I've been talking to some particle physicists, and they take it to be 5.733031 times 10 to the minus 7. Okay, so there's no real agreement on what alpha should be. The other thing is that a p-value can't be used to find evidence in favor. For example, if you think in the continuous case, typically the p-value, when the null hypothesis is true, is distributed uniform 0, 1. So values near 0 are as likely as values near 1. So we can't use the p-value, if it's big, to say, well, we've got evidence in favor. Now, to me, that's absurd. Not that we're using the p-value inappropriately, but just absurd in terms of its inadequacy as a measure of evidence. For example, suppose you're measuring a length, and your units are centimeters. And so you're going to measure the length of this object, whatever it might be, to the nearest centimeter. It doesn't matter how many observations you take. You can never know the true value of the length of that object to anything other than the nearest centimeter. You can't. It doesn't matter. So really the hypothesis is that the true value of this length, I guess I've called it mu 0, I should have called it theta 0, but is in some interval about some numbers of centimeters, plus or minus half a centimeter here. So that's my delta. Delta is a centimeter, right? And what happens to the distribution of x bar as n goes to infinity? Well, sooner or later, all the probability is going to be concentrated in that interval. So we should be able to just look at that and say, oh, we got evidence in favor of the null, of the hypothesis being true. But the p-value doesn't allow us to do that. So we got to fix that somehow, if we can. This criticism of p-values goes back to 1919. There's a paper by a fellow named Boring, a psychologist. And he pointed out, well, there's a real difference between statistical significance and scientific significance. Presumably, the physicist designs their experiment to get the accuracy they want, and they can't get accuracy beyond that from the observations. Another example I really like is due to Cornfield, which is really about sequential, right? If an investigator collects some data and calculates the p-value, they get a value of alpha plus 0.05 plus some small epsilon based on a sample of n1. So they decide to collect an additional n2 data values, and you get a p-value based on the full data set now that's less than alpha. But then it's pointed out that really this is a two-stage or sequential experiment, right? And if you take A to be the evidence against H naught found at the first stage and B to be the evidence against H naught found at the second stage, and calculate what's the probability of finding evidence against H naught at level alpha when H naught is true, well, your p-value, you can never get a p-value less than alpha. This is relevant to something I'm going to talk about in just a minute. But anyway, my overall criticism about p-values as measures of evidence is that we need a measure of evidence that allows us to find evidence in favor. for scientific applications. Now, a recent topic of interest in the statistical literature, you notice a number of papers about E-values. So when I first saw that, E stands for evidence, probably, so I've got to talk about those, right? Well, when I read the papers, that's not what E stands for. It stands for expectation. But anyway, it's still relevant to this discussion. Does it measure evidence properly? Well, what's an E-variable? So we're talking about the same hypothesis again. It's a statistic, n sub psi naught, whose expected value is less than or equal to 1, whenever the null is true. And the observed value of that statistic is called an E-value. And again, you have to specify a cutoff. And here, though, you say there's evidence against H naught when the observed value of the statistic here is greater than or equal to 1 over alpha. And then it's a simple application of this restriction on the expectation of that statistic and Markov's inequality that this gives a p-value that's less than or equal to alpha. So why are people bothering with E-values as opposed to p-values? Well, first I do an example. What is a statistic that you could use? And there's a whole bunch of them, right? And here's a whole class of them, supposedly. I don't work in this area, by the way. But here's a whole class of them, and there's some discussion about what's an appropriate choice of A, right? We just take the usual p-value, raise it to the power A minus 1, and multiply by A. And that's an E-variable for H0. And it has various advantages over p-values. For example, if you look in the literature, I'm going to say what the result is here, but the sequential problem that I just talked about is resolved. And this involves martingale and optional stopping theory. But again, due to the arbitrariness of the cutoff and no evidence in favor, I will submit that E-values are not proper measures of evidence. Now that brings me to my next topic. That's Birnbaum. Birnbaum is kind of a hero because in this area, because he's one of the few statisticians who's really tried to look carefully at the idea or the basic idea of statistical evidence and realize that for a theory of inference, we really do need to characterize statistical evidence more properly. And here's a famous paper in 1962 on the foundations of statistical inference, which caused a lot of controversy. I'll explain what that is. So we look at the set of all inference spaces, which he's in the frequentist domain. So we're talking about all the inference spaces, frequentist inference spaces. And a statistical principle is a relation on this set. And what's a relation? It's just a subset of the cross product of the set of all inference spaces with itself. So, and what does it mean if two inference spaces, I1 and I2, are in a relation? In Birnbaum's formulation, it means they contain the same statistical evidence about theta. And there's several principles. There's the likelihood principle, for example. So we say I1 and I2 are in the likelihood relation whenever the likelihood functions from the two inference spaces are proportional for all theta, right? The sufficiency principle, two inference spaces are in the sufficiency relation if the models have equivalent minimal sufficient statistics. And then there's the conditionality principle. Two inference spaces are in the conditionality relation if there's an ancillary statistic. An ancillary statistic is just a statistic whose distribution does not depend on the parameter. It's fixed. So that one of these inference spaces can be obtained from the other by conditioning on that ancillary. So those are the three main relations that Birnbaum discussed in terms of characterizing statistical evidence. And I will say too, most frequentist statisticians will agree that sufficiency and conditionality are proper characterizations of statistical evidence, and they're somewhat more controversial. Likelihood principle is somewhat more controversial for many statisticians. And what Birnbaum supposedly proved is that if, as a statistician, if you're a frequentist statistician and you accept S and you accept C, then you must accept the likelihood principle. And that's controversial because, of course, S and C are frequentist, whereas the likelihood principle is not. There's no frequentism involved in likelihood. Two inference spaces have the same likelihood function. They may have very different models. So the repeated sampling behavior is irrelevant according to the likelihood principle. Now, people argued about this proof. People tried to disallow his proof, but there's clearly nothing really wrong with his proof. Really, what's wrong with Birnbaum's proof is the statement of the theorem. If you look at it carefully, well, I have a paper on this. It's called "What is the proof of Birnbaum's theorem prove?" And 2013. And what I show there is that the union of these two principles, it's not an equivalence relation. And if you look at Birnbaum's proof, what he actually proved was that the smallest equivalence relation containing S and C is the likelihood principle. Now, that's an interesting result, but it doesn't say you have to accept the likelihood principle if you accept S and C, particularly when you realize another result that says that the smallest equivalence relation containing C is L. And C is not an equivalence relation. S is an equivalence relation. L is an equivalence relation, which they must be if they're going to characterize statistical evidence, right? But C is not an equivalence relation. Neither is SUC. Anyway, so I don't think that result really supports the likelihood principle itself. Now, Birnbaum himself, I don't think did either. And he's wrestled with this for many years. Many of these papers are about the concept of statistical evidence. And in this last paper, he proposed what's called the confidence concept, which is in the context of comparing really two simple hypotheses. And he looked at two error probabilities, alpha and beta, usual error probabilities, and then said, you report alpha and beta as your evidence, measures of evidence, with the following interpretation. You rejecting H naught constitutes strong evidence against H naught when alpha and beta are small, or it's in favor of H1. If it's against H naught, it's in favor of H1. Now, this is not a general definition of evidence, and of course, again, it confounds decision theory with the evidential approach. But I'll come back to talk about this if we've got enough time a little bit later, because it's definitely on the right path. These error probabilities are part of the story, no doubt about it. Now, what about pure likelihood? Well, this is two books, Edwards and Royal, and they based inferences on the likelihood function alone. And the question is, how does the likelihood function characterize evidence? Well, we got this arbitrary positive constant here, C. We want to get rid of it. So we talk about this in terms of the relative likelihood, which means you take the likelihood function and you divide it by the maximum value of the likelihood function at the MLE. And then Royal claimed, if you read his book, that if you get a relative likelihood greater than or equal to 1/8, that means very strong evidence in favor of the null hypothesis, that theta is equal to theta naught. And if it's greater than or equal to 1/32, it represents quite strong evidence in favor of theta true being equal to theta naught. Why 1/8 and 1/32? He has an argument in his book based upon an EARN model, but frankly, I don't find it very convincing. In fact, this comes up in different contexts, and I'll mention another one in just a moment, but it's an attempt to say there's a universal scale on which evidence can be measured. And it's reasonable to ask, does such a scale exist? And there really are no strong arguments to say there is one. Now, there's another problem with likelihood, and that's what happens when you get a many-to-one function. Well, it's not clear how to define the likelihood. What most people use is the profile likelihood, which means you just take the supremum of all, you define the profile likelihood at a value of psi by taking the supremum of the likelihood over all those theta values that lead to that value of psi. There's also less commonly used is the integrated likelihood, where you just average the likelihood function with respect to some probability distribution on the values of theta that lead to psi. So there's two possibilities here. If you look at the location normal, and we want to make inference about the absolute value of theta, well, the likelihood function is given by this quantity here. Well, known and understood. And the profile likelihood is given by what I've written here. And if you look at the density of x bar, it's given by this expression that I've given here. Looks pretty simple, really. It's not as complicated as looks, but what you can discern from that is that the profile likelihood is not proportional to the density, which it must be to be a likelihood function. So the profile is not a likelihood, and in this case, and so profile likelihood intervals are not likelihood intervals, and that's really what we're trying to get at with the likelihood function. We want to say not only evidence for or against, but we want to be able to quantify the accuracy, say, of the MLE. The integrated likelihood is obtained by, if I integrate with respect to probability measures, why I like this example, the nuisance parameter is just the sign of the theta, right? So it's two values. So put probability at 1 of being P and at -1 of being 1 minus P, and you get that's the integrated likelihood. And this comes up again. I've just integrated out the sign. Now, what about Bayesian measures of evidence? So I'm interested in psi. The first step in the Bayesian inference is that I'm going to replace the Bayesian inference base just by integrating out the nuisance parameters. This is the nice thing about Bayesian inference. We know how to handle nuisance parameters. We just integrate them out. And then there's some basic principles of inference, some axioms, if you like. And the first axiom is what I call principle of conditional probability. And we just be in the context of a probability model here for these axioms, because that's what we have when we have a Bayesian. The prior and this density here, m given psi, is what I get by integrating out the nuisance parameter, right? But I've got a new statistical model, if you like, by integrating out the nuisance parameters. But they jointly together give me a probability model for x, and a joint probability model for psi and x. And then the principle of conditional probability tells me if I observe something and I observe x, I replace my initial beliefs, which are given by the prior, by the posterior. And then we have what I call the principle of evidence, though it's not due to me. It's been around for 60 years, at least, or more. In fact, I think it's supposed to be in Keynes' book on probability written in the 1920s. Namely, if the conditional probability is bigger than the initial probability, then the observation that C is true is evidence in favor. If the probability goes down, then we have evidence against, and if they're equal, we have no evidence either way because A and C are statistically independent. And so a valid measure of evidence is going to obey that principle of evidence. And there's various choices one can make. I like what I call the relative belief ratio. I'm going to consider the discrete case here. In the continuous case, we would just take limits, but it's easier to talk about things when everything is discrete. So avoid the math. So the relative belief ratio is just the ratio of the posterior probability of psi to the prior probability. If it's greater than 1, we got evidence in favor, etc. Just like the principle. There's also the Bayes factor. Rather than look at the ratio of the probabilities, the Bayes factor looks at the ratio of the odds in favor, the posterior odds in favor to the prior odds in favor. And the cutoff is the same. So it's both of these are valid measures of evidence. Also, you could look at the difference between the posterior probability and the prior probability and take the cutoff to be 0. There are many different valid measures of evidence, but the relative belief ratio has a lot of positives for it. In particular, the Bayes factor can be obtained from the relative belief ratio fairly easily. Now, so what's the evidence concerning the null hypothesis that psi is equal to psi naught? Well, I've immediately got the relative belief ratio, and that tells me whether I've got evidence for or against. But I have to measure the strength as well. How am I going to do that? Well, how do we measure the strength? Well, the evidence is telling us something. It's saying we've got evidence that psi naught is true, or I've got evidence that psi naught is false. Well, I'm going to measure the strength of that evidence by measuring how strongly I believe what the evidence says. And I'm going to do it via this posterior. There's different ways to measure the strength as well, but most commonly this works. The measure is calculating this posterior probability, because when this is less than 1, I want this to be a small probability, because that posterior probability is, say, if it's small, is telling me, well, my belief that the true value has a bigger relative belief ratio is quite big. If this is bigger than 1, I want this probability to be big, because that's telling me, well, if my belief that the true value has an even bigger relative belief ratio is small. Now, what about the Bayes factor? And this is where one of my disagreements with the usage of Bayes factors in the literature. There's a scale due to Jeffreys. And what people do, they calculate the Bayes factor, and then they appeal to this scale. By the way, I've stated the scale here for evidence in favor. For the evidence against, you just take reciprocals here. And you say you look at where the Bayes factor is in this scale, and you say, well, if it's over 100, for example, very strong evidence. Now, the fact of the matter is I can construct examples where the Bayes factor is 1,000,000. And yet, when we calculate how strongly we believe what the evidence says, not even used just by just a two-valued hypothesis parameter psi, we don't believe what the evidence says. So this scale is not, and its derivatives are I don't believe they're correct. Again, it's an attempt to say there's a universal scale in which evidence is measured. And as I said, it's easy to construct examples where the Bayes factor or the relative belief ratio is very high, but the posterior probabilities are very small. And I'll refer to you to this paper here. It's on my website. Now, what about for inferences based on this measure of evidence? What have we got? The relative belief estimate, which we just find the value that has the most evidence in its favor. So we maximize the relative belief ratio. And to assess its accuracy, we calculate what I call the plausible region. It's just a set of values that have evidence in their favor. We look at its size and we calculate its posterior probability, which measures how strongly we believe the true value is in that set. Now, there's another issue, and that's bias, which most Bayesians ignore, which I don't think they should. And that is, I ask the question, well, a priori, what's my probability of getting evidence? Two biases. There's bias against and bias in favor. Bias against the null hypothesis here is I ask the question, before I even see the data, what's my prior probability that I don't get evidence in favor of psi naught being true? So this is an error probability. This goes back to Birnbaum's idea, if you like. And what about bias in favor? Well, suppose the null hypothesis is meaningfully false. That's my delta, the delta that I was referring to earlier. What's the probability I don't get evidence against when psi naught is meaningfully false? And you want those to be small. Those are the error probabilities, a priori. So these are designed. We don't do them based on the observed data. Before we collect the data, we calculate these things to see how reliable our inferences have got to be. And the nice thing is you can prove that these things converge to zero as you increase the amount of data. So you can design your experiment to make sure the biases are small. These are biases for the hypothesis testing problem. There are also biases for estimation in terms of coverage probabilities, but I won't say what those are. Almost done, just last slide, almost last slide. The parameter of interest is the absolute value. Well, the relative belief ratio is basically proportional to the integrated likelihood, right? It's not, it can't be multiplied by a constant, positive constant, because that would destroy the cutoff, right, as a measure of evidence. Now, there's another famous example of Jeffrey, which I think shows why we have to calculate biases. The Jeffreys-Lindy paradox. Suppose I want to test that the mean of the location normal is psi naught, theta naught, and I use the z-test, right? And suppose I observe 5. So I'm 5 standard deviations away, and that's the one the particle physicists use, so I get this p-value, very small p-value. What happens to the Bayesian, the relative belief ratio or the Bayes factor? They're equal in this case, as it turns out. Well, as the variance of the prior tau naught here goes to infinity, these two quantities converge to infinity. So it looks like I'm getting over, in terms of Jeffrey's scale, for example, I'm getting overwhelming evidence in favor of the null hypothesis. But actually, when you compute how the strength of that evidence, as tau naught goes to infinity, it goes to the z-test p-value. So this will be very, very weak evidence in favor. Now, that's a partial resolution of the problem, but really to resolve Jeffrey's paradox, you've got to go to the bias calculations. Because what you can show there is that the bias in favor goes to 1 as tau naught goes to infinity. So to fix that problem, what you got to do is you want to pick your tau naught squared. You want to be uninformative. That's the idea. about choosing a big tau naught square. Okay, choose it, but don't choose it to be unrealistically large, and then choose your sample size to make the biases small. So my conclusions. So I think in frequentism, one can say that it has not been successful to this point to find a clear characterization of what we mean by statistical evidence. We need a prior, and we don't need a loss or a utility. Well, how do we choose models and priors? And David was just talking about this a few minutes ago, elicitation for priors. That's the right way to do it. Both models and priors are falsifiable, so I think the issue about subjectivity is a red herring. Bias calculations are essentially frequentist in nature, sometimes exactly so. So these form a link between frequentism and Bayesianism, which are supposedly incompatible. Not so. That's not true. What about relative belief in decision theory? Now, there's a recent paper by myself and Glenn John. And basically what we show there is that you can generate relative belief inferences within the decision theoretic context. How? Well, let's suppose we have a finite set of values for psi, say in a classification problem. We'll take your loss function to be 1 over the prior, effectively, except when you get the answer right at 0. Otherwise, it's so if you're in the tail, if the truth is in the tails of the prior, you've got big losses, but not otherwise. And or in the infinite case, you take your loss a sequence of loss functions where you bound the loss by 1 over eta here, and let eta go to 0. And then you can prove that the relative belief ratio, well, the relative belief inferences arise exactly from this loss function, and they arise, well, there are different contexts. In the case where you have countable parameters, they arise exactly from this loss function, or as a limit of the Bayes rules from these loss functions as eta goes to 0. And in fact, what this says is that in practice, relative belief estimates with respect to this loss function are optimal and admissible. And I'll stop there. Thank you. Hopefully I didn't go too much over time.
Is it over, sir? So it is open for the questions, please. Anyone who has got any query or the questions?
The paper's on my website, by the way, and if you're interested in that. David.
Well, that was lovely, Mike. My concern in this general area is that I rarely believe the model. And it seems to me that all of your work requires that you actually believe that you have a normal model or whatever.
Well, it doesn't have to be a normal model. But yes, there will be. There is a model. Yes, there are. If you can do inference without ingredients, great. I don't know.
Yep.
Now, if you want to be non-parametric Bayes or something like that, there's no problem. It doesn't depend on some parametric model being there. So there are inputs into the story. And if I can get rid of them, I would. But the restriction on the inputs is they always have to be checkable against the data, right? Falsifiable, in other words. But so then the example is normal because that's simple. Right?
Sure. I realize the normal is just a case in point, but
yeah, that's right.
Thank you.
Any other, please? Anyone who has any query? Sir, can I ask something from you?
Sure.
So because I was not knowing about the concept of E-value, you are just talking about the E-value evidence-based. So once we had just
in the evidence-based idea, but for a while I thought E stood for evidence. But I've been corrected by a person who works in that area. E stands for expectation. P-value, P stands for probability. And E-value, E stands for expectations.
Expectations, okay. And the Jeffreys Bayes factor, so you say only way, is it the only way to improve the strength of the evidence, or we can have anything else?
My assertion is that you have to calibrate relative belief ratios. You have to calibrate Bayes factors. You could calibrate the Bayes factor in the same way that I calibrated the relative belief ratio. No problem. Now, there's another issue with Bayes factors, and that's in the continuous case. And what people are currently doing, if you have a null hypothesis that has prior probability 0, they modify the prior and take a mixture prior. This causes issues, right? And there's a paper on my website about this. You don't need to do that. If you take a limit, instead of putting that discrete mass at a point, the base factor is actually equal to the relative belief ratio. So I think Jeffrey should have defined the base factor to be the relative belief ratio, to be frankly. But people have called the relative belief ratio, by the way, other names. I call it the relative belief ratio, but it has existed in the literature. It's not for many years. It's not just due to me.
So anyway, anyone else? So if no questions, so we must thank the speaker for very nice, interesting lecture.
Thank you.
Thank you, sir. Thank you, sir. Over to you, Professor Satish.
Yeah, thank you,
Oh, there is a question.
Professor Evans, for your wonderful talk. Thank you so much. Also, we are thankful to the Sangeeta Arora, Professor Arora, for chairing the session in a very nice way. Thank you so much. In fact, we had today we can conclude the sessions, all the sessions today.
Good night from our side.
Yeah, now it is 9:30. Yeah, 9:29.
Well, thank you for staying up.
Yeah. Tomorrow morning we can let us start the tomorrow's session at 9 itself. So please, all those who are interested to join that way, please join before 9, 8:30 to 9 entering time. Please, your support is main factor behind the success of the event. Thank you so much. Thanks a lot to all speakers and delegates. And thank you all. Thank you so much. Good night and bye.